Hey, David here. We are live for another public study session on the multiple truth hypothesis, the history of science, the scientific method. What is science? The philosophy of science. Interesting topic is going to be extremely important for what eventually is going to be hopefully publishing my research and maybe even a book on the multiple truth hypothesis. So, um, just show real quick. Last stream, I started this new series and I basically just purely read from various articles, Wikipedia, and the Stanford Encyclopedia. And I just wanted to jump right in and I wanted to get some generic research out there. So I went through the Wikipedia on the philosophy of science, and then the historiography of science, and the history of the scientific method, and Thomas Kuhn's Structure of Scientific Revolutions, all of that from Wikipedia. And then from the Stanford Encyclopedia, Plato, I went through Hobbes' Philosophy of Science and Theory and Observation in Science. And I have a lot more articles. So as you can see, I have, just in this folder, Science and Philosophy, quite a few more things. Like I could probably go, maybe even more than 5 episodes. It's a huge topic, and we'll see how much is relevant to what I'm trying to do. So before I start going into reading, and hopefully today will be less of me straight reading, but will be more explanation, more moving forward to what is this multiple truth hypothesis, how does it relate, and you'll see why it's important that it be grounded within the scientific framework. And so today I have lined up to talk about the scientific revolution in terms of like Galileo and Newton and the foundation of Western science. I'm going to talk about John Locke's philosophy of science. I'm going to look at Wikipedia pretty exhaustively, the scientific method. What does the scientific method entail? We'll look at what's called scientific representationism, which is a little bit about what is a scientific representation in terms of a model. And we'll get more into model theory at a certain point. This might become pretty intense. It might be mostly like logical notation and mathematical, and get more scientific. And then I'm going to look at Kant's philosophy of science. Kant is probably one of the most important figures that we're going to talk about, and is actually important for a whole bunch of things in terms of consciousness, philosophy of mind. But in terms of the philosophy of science, Kant is extremely important. Coming to the Vienna School, which maybe Einstein's part of, and hopefully we're going to look at Einstein's philosophy of science, and then also the Neo-Kantians in the Marburg School, which I think Duvid would more fall into a Neo-Kantian of the Marburg School. I've talked about this on Week in Review, and we will go back to the Marburg School and Neo-Kantianism. And hopefully we'll also look at the philosophy of technology in terms of connection between science and technology. So you're just thinking last week and some of the conversations we had, the biggest difficulties that I think a lot of people have is philosophy of science is not science. And it's hard to understand what science is. And the philosophy of science is more the explanation of what science is, but scientists are not philosophers. And as we're going to see today, modern science is basically, in terms like the meaning science just means knowledge. And we get into technology. Maybe at some point I'll look more to like the ancient Greeks, but there's the epistemology of knowledge that also has the general word science. There's certain Greek words like there's certain Greek words like um, like episteme and techne, which are forms like knowledge and know-how. What we call like theoretical knowledge and know-how knowledge, and technology, like techne, could be like an art form. Like I said, like technocrat is general know-how, knowing how to do things, versus theoretical knowledge. And theoretical knowledge is closer to what we're going to call science, as like a pure science, knowing how things work, versus so I apologize, just sold a book on eBay. So there's theoretical science of knowing how things work. Theoretical science of, hey, Claire, thanks for tuning up. Yes, Claire's saying science is a methodology, relatively. So science today, because the term science has multiple meanings. And science is basically what's produced by the methodology of the scientific method. And yeah, Shiva, thanks for tuning in. And the purpose really of the scientific method is to divorce what became science from metaphysics and from philosophy. So that's why I said, like, people who are involved in the philosophy of science is usually separate. In fact, you'll find that the majority of the big philosophers of science are not actually scientists; they're philosophers, and they're concerned with metaphysics. Like I saw, like a Shesh Delela in these various posts on metaphysics, and he's saying like, well, the why, and science doesn't really answer those questions. And even the questions of like, what is mass, what is space, is meant to be separated from science. And so, Duvid, I guess I'll call myself a scientist sometimes, but my theories are, I'm probably more a metaphysician. And so, like, I'm talking about metaphysics. It has bearing on science. And the multiple truth hypothesis is hopefully helpful to navigate this, because see, there's a lot of unknowns, and science could push forward despite the unknowns. But just within, so to say, science and methodology, there's use of the scientific method. And then when you get into things like the hard problem of consciousness, psychology, where there's much more unknowns, many more necessity of metaphysical basis. On Week in Review, we discussed this at length about mind independence and the conceptual framework of Galileo, that science is the measurement and method of relationships in the material realm, and it's mind independent. If you could reject the metaphysics of if there is such a thing as mind independence, does there exist, which comes from the Cartesian dualistic system, and science is in the realm of the material realm, and science to some extent has nothing to say about the non-material realm. But then we mentioned last week Hobbes, and Hobbes has a little bit of the precursors for materialism. Yeah, so clearly metaphysics is, you're talking about abstract ideas and the definition of concepts like what is space, what is time, what is mass, energy, what's the relationship between mind and energy. There's hard borderlines. All these are Greek terminology: philosophy, metaphysics, ontology, science. All these come from various Greek terms. But generally, science is grounded in metaphysics. However, it's not necessarily to be grounded in metaphysics to do science. You could just jump straight in and do science without being metaphysically grounded. And metaphysics cannot be proven by the scientific method in the same way that science itself can. Although science informs metaphysics, and likely metaphysics informs science. So we see also that there's schools in the philosophy of science that science itself is supposed to be completely divorced and independent from metaphysics. So I told Jennifer Shishtalela that they're essentially making a category error when they focus on metaphysics or the philosophy of science. And metaphysics and the philosophy of science is not science. And you could try to understand, well, what is science from a metaphysical understanding of science? And then what benefit is there to metaphysics? And various complicated questions that I'm going to pivot back to. And this is going to be a long journey, probably at least maybe even like 10. I might even do a full like 10 episodes on this. So there's a lot. If I take this all the way to philosophy of mind and the hard problem of consciousness and all the various issues, it might even be like 10 episodes because there's a lot of material. So I have a lot of reading today. I'll probably do a little bit more commentary. I want to be fully grounded within the Western canon, and we'll see. We'll talk a little bit about this because in many ways, science is the story of, God forbid, dead white men. And if we saw last week in the historiography of science, you have the internalist approach and the externalist approach. And the internalist approach, which isn't just for the historiography of science, but historiography in general, is the progression of ideas independent of the culture and place where it occurs. Just saying a natural progression of ideas building off of prior ideas. And then the externalist approach of the historiography of the history of science takes into account the time and place and culture through which these ideas arose. And you really need both. And you might need like the multiple truth hypothesis is, okay, now I'm giving an internalist approach, and now I'm giving an externalist approach. And then we'll talk about the canonization. Probably not today. We'll touch upon it briefly, like the idea of measurement in science. So all cultures have methods of measurement. The Bible has its own measurement system. A lot of times measurement systems are based on human anatomy, like, the Bible and Jewish law, you have the Amma and the various sizes that are generally in correspondence to a person's body size, to later having a canonization of measurement in terms of standardized objects like the meter, like the metric system, and what arose in the West, Freemasonry, the role of the Royal Society. These are all topics I want to pivot back to, and I might touch upon them today, but largely I want to read through. I want to get through a lot of material. I just want to put some of this stuff out there to show what I'm working with in terms of building upon the current canon. And it's kind of like God forbid the history of dead white men. To some extent you have to pound through that. So like even tens of hours, because science in essence is the history of dead white men. And almost all the name are called the blue-eyed men, the European men, a handful of Ashkenazi Jews, but from the conception of modern science really till the World War II period, it's all centralized in Europe, and it's almost all centralized to the various royal societies and academies of science. And we talked a little bit about that yesterday, about the Academy of Science. I went into in a week in review, and hopefully we're going to pivot back to that. I'm going to mention John Locke. And when I get to John Locke, we're going to see I'm going to talk about the effect of the scientific method upon all fields, and how history, politics, many things, aspects of the scientific method have been applied to all fields, but they're not scientific. And we're going to look at Kant's philosophy of science. We're going to look at Kant's criticism of chemistry and saying that chemistry is not a science. And then the special questions of biological sciences, and then possibly the scientific method applied to anthropology, psychology, and history. And, Claire, history is very important to her. And like a scientific understanding of history. Your average person doesn't really care about science that much. It's more technology and the gadgets. And I'm going to talk about the philosophy of technology. because most of the philosophy of science, most people who focus on the philosophy of science are actually theologians. Like in Western secular science, there's a school of the philosophy of science that has some secular studies, like in university departments, but the vast majority of the people who focus on the philosophy of science are actually theologians, non-scientists that have theological purpose. And the reason they focus on the philosophy of science is to clearly delineate the border of science and say, this is what science could define, this is what science cannot define, and hence this is where theology and religion steps in. And there's an appeal, probably especially among Hindus, among some Kabbalists, although to try to partake science and say the metaphysics is actually scientific, that the metaphysics and science is one of the same. But we'll see that generally the Western conception of science tried to completely divorce metaphysics from science. So therefore, the Eastern systems are at odds with the scientific method, and the terminology science, even the terminology of, are you practicing metaphysics or science? Hey, John, thanks for tuning up. Good to see you. And then also, when I pivot back to philosophy of mind, where it was I want a working system to say, well, science could only go so far. And like I was talking the last program about Kuhn's scientific revolutions, where there's a lot of anomalies in the data. There's a lot of things that cannot properly be described by the known theories, specifically in philosophy of mind, consciousness. And so if you're coming on to, so to say, a non-scientific idea that is not within the boundary of the scientific method, how can you combine those type theories? And that's where the multiple truth hypothesis will come in handy, where you like dualistic systems. And then there's also questions about mathematics and logic, and the role of mathematics and logic, and symbolic, and hopefully we'll get to the models. And after I cover this precursor data, a lot of this stuff is going to be focusing on this concept of models and what is a scientific model. And we're going to constantly be coming back to this problem between metaphysics and science. What is the border between metaphysics and science? And so that's going to be extremely important. So let me make a blessing. So this is going to be mostly me reading, because I want to get this basic information out there, and I want my information fully grounded. So when I'm talking about these issues, that we'll see that they're fully grounded within the scientific tradition, or at least I say if I'm saying something different, that I'll be able to place it within the larger schools of science and the border, so it doesn't become unclear. And then also, like, all the debates or conversation that I would say almost everybody commits these category errors. And so I'll mention this one last thing. So the multiple truth hypothesis, I'm focusing on the concept of truth. And so science makes truth claims, but truth claims are not unique to science. Something could have a truth claim just because it follows logic, or we say the facts in politics. You could have statements that like syllogism and the inductive and deductive method are not unique to science. You could use those purely in the realm of ideas and logical formulations of non-scientific elements. And those statements would also have truth claims, like to say, my name is David. And you say, well, there's a truth claim to that. And it's not a scientific claim, or historical claims. And we'll talk about that a little bit with Locke and Kant, about the concept of truth in science, and is science actually making a truth claim? And then how do the truth claims made by science differ from the truth claims of other fields? like a fact check in politics. You say, well, I fact check that. Like, the politics, like, Israel, Palestine, or Ukraine, Russia. What's the facts? And well, is it scientific? And you say, well, so it's complicated, and it's another subject I'm going to pivot back to after we clearly define the boundaries of science, to define the boundaries of truth, and to say that no, I mean, truth is not only part of science. In fact, truth does not even derive from science. Truth largely derives from philosophy and ontology, uh, as opposed to science. In essence, most philosophers of science would not even say that science is making truth claims. However, there's the contemporary usage of science, the societal respect or value towards science, and the dependency upon technology, living in a technologically adapted world. And so it's very complicated. There's a lot of issues. So with that, let me just jump right in and just clear out there the multiple truth hypothesis is not making a distinction between fact and opinion, because the claim is that we don't really know what the truth is. If you want to put it, eventually it'll be in a mathematical terminology. Like if you want to say fact is 1, has 100% value, and falsehood has a 0 value, and truth claims cannot be delineated as true or false. As we'll see, when we get more in depth into the scientific method, truth claims can only be delineated as more or less probable, and they could possibly even be estimated some sort of value between 0 and 1, a percentage of likelihood and unlikelihood. Like Tinkle saying, similar to like the Schrodinger wave equation, that the wave equation collapses and you have a value, like so to say, with truth. And so if you have like the theory of gravity, uh, a scientist wouldn't tell you the theory of gravity is 100% truth claim, or even that the theory of gravity is true. It has a statistical value, a truth value. So truth from Aristotelian logic could have a truth claim where it's true or false. That would be like a 1 or 0, or in game theory. So the multiple truth hypothesis is a recognition that truth is something, and we'll see this also with Kant's philosophy of science, where there's a recognition that we can't actually know the truth. In Locke and a lot of the main philosophers generally accept that truth is elusive due to the problem of empiricism, to the human form. Theologically, say there might theoretically be a truth, that there is a fundamental truth and God knows the truth, but that truth is beyond our ability to know. However, that's not relativism. Some things are more true than others. And so science itself has a way of dealing with material phenomenon. And then there's other tools of logic and possibly mathematics and other methods that could be used for truth in non-scientific fields. And we'll see a little bit of that today when I talk, especially about John Locke. When I talked about Hume the other day, about Hobbes, Thomas Hobbes, claimed to have like a science of politics. As the scientific method came out, and even till today, people, for whatever reason, think that it adds more validity to their claims to say it's scientific, as opposed to saying like, no, I'm talking metaphysics, not science. That for whatever reason, science has a certain credibility factor that people like to guise their claims within science, probably to add credibility. But I'm trying to correct that category error and say, actually, if you're talking metaphysics, just talk metaphysics. That you could have truth claims within metaphysics and to navigate these various factors. So today I give a longer introduction because this is pretty complicated, and the reason I'm doing this is really to advance my own theories. But I want to stay high within the realm, so to say, of accepted scholarship. And so I'm going to look at first the scientific revolution, and just a historical background understanding So I've been using this extension super simple highlighter. Claire, you might find this useful also. But yeah, this program, this app that allows me to highlight, and so hopefully that makes it more useful. It's been, I've been finding it interesting. Hopefully, it makes it easier for people to follow along. Okay, scientific revolution. The scientific revolution was a series of events that marked the emergence of modern science during the early modern period, when developments in mathematics, physics, astronomy, biology, and chemistry transformed the views of society about nature. The era of the scientific renaissance focused on, to some degree, on recovering the knowledge of the ancients and is considered to have culminated in the 1687 Isaac Newton publication Principia, which formulated the laws of motion and universal gravitation, thereby completing the synthesis of a new cosmology. Great advances in the science have been termed revolutions since the 18th century. For example, 1747, the French mathematician Alexis Claude Clairaut wrote that Newton was said in his own life to have created a revolution. The word was also used in the preface to Antoine Lavoisier's 1789 work announcing the discovery of oxygen. Few revolutions in science have immediately excited so much general notice as the introduction of the theory of oxygen. Lavoisier saw his theory accepted by all the most eminent men of his times and established over a great part of Europe within a few years from its first promulgation. In the 19th century, William Whewell described the revolution in science itself, the scientific method that had taken place in the 15th and 16th century. Among the most conspicuous of the revolutions, which opinions of this subject have undergone, is the transition from an implicit trust in the eternal powers of man's mind to a professed dependence upon external observation, and from an unbounded reverence for the wisdom of the past to a fervid expectation of change and improvement. This gave rise to the common view of the scientific revolution today. Whewell also, I've shared his books on Week in Review, but Whewell's actually the coiner of the term scientist, in terms of scientist as a person who follows the scientific method. A new view of nature emerged, replacing the Greek view that had dominated science for almost 2,000 years. Science became an autonomous discipline, distinct from both philosophy and technology, and came to be regarded as having utilitarian goals. Scientific revolution is traditionally assumed to start with the Copernican revolution, initiated in 1543, and to be completed in the grand synthesis of Isaac Newton's 1687 Principia. Much of the change of attitude came from Francis Bacon, whose confident and emphatic announcement in the modern progress of science inspired the creation of scientific societies such as the Royal Society. And that'll be a topic I'll be returning to in detail, the Royal Societies and Freemasonry. The scientific revolution was enabled by advances in book production. Before the advent of the printing press, introduced in Europe in the 1440s by Johannes Gutenberg, there was no mass market on the continent for scientific treatises, as there had been for religious books. Printing decisively changed the way scientific knowledge was created, as well as how it was disseminated. It enabled accurate diagrams, maps, anatomy, anatomical drawings, and representations of flora and fauna to be reproduced, and printing made scholarly books more widely accessible, allowing researchers to consult ancient texts freely and to compare their own observation with those of fellow scholars. And in reality, Isaac Newton, 200 years after the printing press, still mostly copied out books, that he had a few access to books, but even 200 years after the printing press, Newton was still largely copying by hand the few books on science that he had access to. The ability to access previous scientific research meant that research did not have to always start from scratch in making sense of their own observational data. In the 20th century, Alexander Koyré introduced the term scientific revolution, centering his analysis on Galileo. The term was popularized by Herbert Butterfield, and Origins of the Scientific Method. Thomas Kuhn's 1962 work, The Structure of Scientific Revolutions, emphasized that different theoretical frameworks, such as Einstein's theory of relativity and Newton's theory of gravity, which it replaced, cannot be directly compared with meaning loss. So anyone's been following Week in Review, I have been sharing and going over many of these names and their books over the last few months on Week in Review, which this week should be tomorrow night, Thursday at 7 p.m. Eastern Time. The period saw a fundamental transformation in scientific ideas across mathematics, physics, astronomy, and biology in institutions supporting scientific investigations, and the more widely held picture of the universe. The scientific revolution led to the establishment of several modern sciences. Empiricism. By the start of the scientific revolution, empiricism had already become an important component of science and natural philosophy. Prior thinkers, including the 14th century nominalist philosopher William Ockham, had begun the intellectual movement toward empiricism. The term British empiricism came in to describe philosophical differences perceived between two of its founders. Francis Bacon, described as an empiricist, and Rene Descartes, who was described as a rationalist. Thomas Hobbes, George Berkeley, and David Hume were the philosophers' primary exponents who developed a sophisticated empirical tradition as the basis of human knowledge. An influential formulation of empiricism was John Locke's An Essay Concerning Human Understanding, 1689, in which he maintained that the only true knowledge that can be accessible to the human mind was that which was based on experience. He wrote that human mind was created as a tabula rasa, a blank tablet, upon which sensory impressions were recorded and built up knowledge through a process of reflection. And today I will be going somewhat in depth into John Locke, who was a contemporary and friend of Isaac Newton. Francis Bacon. The philosophical underpinnings of the scientific revolution were laid out by Francis Bacon, who has been called the father of empiricism. His work established and popularized inductive methodologies for scientific inquiry, often called the Baconian method or simply the scientific method. His demand for a planned procedure investigating all things natural marked a new turn in the rhetorical and theoretical framework for science, much of which still surrounds conceptions of proper methodology today. As Claire said, science today is basically a methodology. Bacon proposed a great reformation of all process of knowledge for the advancement of learning, divine and human, which he called the Great Instauration. For Bacon, this reformation would lead to great advancements in science and the progeny of inventions that would relieve mankind's miseries and needs. His Novum Organum was published in 1620, in which he argues man is the minister interpreter of nature. Knowledge and human power are synonymous. Effects are produced by the means of instruments and helps. Man, while operating, can only apply or withdraw natural bodies. Nature internally performs the rest. And nature can only be commended by obeying her. Here's an abstract of the philosophy of his work, that by the knowledge of nature and the using of instruments, man can govern and direct the natural work of nature to produce definite results. Therefore, that man, by seeking knowledge of nature, can reach power over it and thus reestablish the empire of man over creation, which has been lost by the fall together with man's original purity. In this way, he believed, would mankind be raised above conditions of helplessness, poverty, and misery, while coming into a condition of peace, prosperity, and security. For this purpose of attaining knowledge of power over nature, Bacon outlined in this work a new system of logic he believed to be superior to the old ways of syllogism, developing a scientific method consisting of procedures for isolating the formal cause of a phenomenon through eliminative induction. For him, the philosopher should proceed through inductive reasoning from fact to axiom to physical law. Before beginning this induction, though, the inquirer must free his or her mind from certain false notions or tendencies which distort the truth. In particular, he found that philosophy was too preoccupied with words, particularly discourse and debate, rather than actually observing the material world. For while men believe their reason governs words, in fact, words turn back and reflect their power upon the understanding, and so render philosophy and science sophistical and inactive. Bacon considered that it is the greatest importance to science not to keep doing intellectual discussions or seeking merely contemplative aims, but that it should work for the bettering of mankind's life by bringing forth new inventions, even stating inventions are also, as it were, new creations and imitations of divine works. So, see, in the creation, when I pivot back to the Royal Society and the creation of science, science had a utilitarian factor related to advancements in technology that theoretically were supposed to benefit mankind. And you'll see that modern science has maybe separated that optimism from science to being purely a method, and the question of the truth claim, the relation of the truth claim to science to the utility of science. Scientific experimentation. Bacon first described the experimental method. Galileo Galilei had been called the father of modern physics. The observational astronomy, his original contribution to science of motion, were made through an innovative combination of experimental and mathematics. Galileo was one of the first thinkers to clearly state that the laws of nature are mathematical. In the Essayer, he wrote, "Philosophy is written in the grand book, the universe. It is written in the language of mathematics, and its characters are triangles, circles, and other geometric figures." His work marked another step towards the eventual separation of science from both religion and philosophy, a major development in human thought. He was often willing to change his views in accordance with observation. In order to perform his experiments, Galileo had to set up standards of length and time so that measurements made on different days and in different laboratories could be compared in a reproducible fashion. This provides a reliable foundation on which to confirm mathematical laws using inductive reasoning. Galileo showed an appreciation for the relationship between mathematics, theoretical physics, and experimental physics. He understood that the parabola, both in terms of conic sections and in terms of the ordinate varying as the square of the abscissa. Galileo further asserted that the parabola was the theoretical ideal trajectory of a uniformly accelerated projectile in the absence of friction and other disturbances. Mathematization. Scientific knowledge, according to Aristotelians, was concerned with establishing true and necessary causes of things. To the extent that medieval natural philosophers used mathematical problems, they limited social studies to theoretical analysis of local speed and other aspects of life. The actual measurement of physical quantity and the comparison of those measurements to a value computed on the basis of theory was largely limited to the mathematical disciplines of astronomy and optics in Europe. In the 16th and 17th century, European scientists began increasingly applying quantitative measurements to the measurement of physical phenomena of the Earth. Galileo maintained strongly that mathematics provided a kind of necessary certainty that could be compared to God's with regard to the few mathematical propositions which the human intellect does understand. I believe its knowledge equals the divine in objective certainty. Galileo anticipates the concept of systematic mathematical interpretation of the world in his book Psychotore. Philosophy is written in a grand book, the universe, which stands continually open to our gaze, but it cannot be understood unless one first learns to comprehend the language and interpret the characters in which it is written. It is written in the language of mathematics, and the characters are triangles, circles, and other geometric circle figures, without which it is humanly impossible to understand a single word in it. Without these, one is wandering around in a dark labyrinth. In 1591, Francis Viete published In Atrem Analyticum Isagoge, which gave the first symbolic notation of parameters in algebra. Newton's development of infinitesimal calculus opens up new applications of the methods of mathematics to science. Newton taught that scientific theory should be coupled with religious experimentation, which became the keystone of modern science. Mechanical philosophy. In mechanical philosophy, no field or action at a distance is permitted. Particles or corpuscles of matter are fundamentally inert. Motion is caused by direct physical collision. And this concept of mechanical philosophy is going to be extremely important to the philosophy of science. What is matter? What is space? And the dividing line for what is science and what is metaphysics. And you will be coming back to this quite often, although I'm not going to veer too much into these philosophical, metaphysical questions on what is matter. Institutionalization. The first moves towards the institutionalization of scientific investigation and dissemination took the form of the establishment of societies where new discoveries were discussed, and published. The first scientific society to be established was the Royal Society of London. This grew out of an earlier group centered around Gresham College in the 1640s and 50s. These physicians and natural philosophers were influenced by the new science as prompted by Bacon in his New Atlantis from approximately 1645 onwards. A group known as the Philosophical Society of Oxford was run under a set of rules on the 28th of October in 1660. The 1660 Committee of 12 announced the formation of the College for the Promoting of Physical, Mathematical, Experimental Learning, which would meet weekly to discuss science and run experiments. At the meeting, Robert Moray announced that King Charles approved the gatherings and a royal charter was signed on the 15th of July, 1662, creating the Royal Society of London, with Lord Bronchier serving as the first president. A second royal charter was signed in the 23rd of April, 1663, which the king noted as the founder and with the name the Royal Society of London for the Improvement of Natural Knowledge. Robert Hooke was appointed as the curator of experiments in November. The initial royal favor has continued, and since then, every monarch has been a patron of the society. The society's secretary was Henry Oldenburg. Its early meetings included experiments performed by Hooke and then by Dennis Poppin, who was appointed in 1684. These experiments varied in their subject area and were important in some cases and trivial in others. The society began publications of philosophical transactions in 1665, the oldest and longest running scientific journal in the world, which established the important principles of scientific priority and peer review. The French established the Academy of Sciences in 1666. In contrast to the private origins of its British counterpart, the Academy was founded as a government body by Jean-Baptiste Colbert. Its rules were set down in 1699 by King Louis XIV when it received the name the Royal Academy of Sciences, which was installed in the Louvre in Paris. Hey, Memes, thanks a lot. God bless. Appreciate that. Appreciate your support, and definitely appreciate your content too. Glad to see you past 1,000 subs, and you've been doing more of these similar just public study sessions like Stephen Wolfron. I think these public study sessions, conversations are important, but these public study sessions are extremely important for ourselves and for people just like accuracy, due diligence. So props. Mechanical devices. And we'll see also that this is going to play a huge part in science, the interplay between science, engineering, and mechanical devices, measurement devices. I talked about last time the entry on observation and theory, and where observation these days is mostly instrumentally aided observation. Very rarely does a person just do plain observation. Almost always observation is aided by mechanical devices, let alone computational aids like the computer. All topics, like I said, like this might even be like a 10-part series. I'm just looking at all the stuff that goes into it. But I want to clearly lay out today, I'm going to go in detail too on the scientific method, just the precursors. What is the scientific method? What's the background of science? And then we're going to see it's overwhelming. The philosophy of science and all the various thinkers and names and ideas, let alone the science itself. Keep on mentioning the philosophy of science is not actually science. Mechanical devices. As an aid to scientific investigation, various tools, measuring aids, and calculating devices were developed in this period. Calculating devices. John Napier introduced logarithms as a powerful mathematical tool with the help of Henry Briggs. Their logarithmic tables embodied a computational advance that made calculations by hand much quicker. His Napier bones used a set of numbered rods and as a multiplication tool using the systems of lattice multiplication. The way was opened to later scientific advances, particularly in astronomy and dynamics. At Oxford University, Edmund Gunter built the first analog device to aid computation. The Gunter scale was a large plane scale engraved by various scales or lines. Natural lines such as the line of chords, the line of sines, and tangents are placed on one side of the scale and the corresponding artificial logarithmic ones on the other side. This calculating aid was a predecessor to the slide rule. It was William Oughtred who first used two scales sliding by one another to perform direct multiplication and division, and thus is credited by the inventor of the slide rule in 1622. Blaise Pascal invented the mechanical calculator in 1642. The introduction of his Pascaline in 1645 launched the development of mechanical calculators first in Europe and then all over the world. Gottfried Leibniz, building on Pascal's work, became one of the most prolific inventors of the field of mechanical calculators. He was the first to describe a pinwheel calculator in 1685, and he invented the Leibniz wheel used in the arithmometer, the first mass-produced mechanical calculator. He also refined the binary number system, the foundation of virtually all modern computer architectures. John Hadley was the inventor of the octant, the precursor of the sextant, invented by John Bird, which greatly improved the science of navigation. So there's a direct correspondence between the history of technology and invention. And A. Leader, good to see you. Thanks for tuning in. And science. And just to mention, my grandfather, who went to the University of Missouri and got a degree in geological engineering, used a slide rule. And we were talking a week in review about Noam Chomsky, who was part of the cognitive revolution in the 40s with Herbert Simon's introduction to information theory. And I'm going to probably talking at length about Alan Newell and Herbert Simon, who are also extremely important in the philosophy of science and computation and various things. But Noam Chomsky, who just wrote in the New York Times op-ed about ChatGPT, was at MIT before computers when they were first introducing vacuum tube computations. And so, I still, God bless my grandfather's slide rule. My father was trained as a kid on a slide rule. They had calculators, but they were expensive. And my father in high school was trained on a slide rule. So the advent of modern computers and computation, has changed things quickly. But you're just thinking like Noam Chomsky in his late 90s now was at MIT in the 40s when computers were just coming out and when they were still using vacuum tubes. So this is important to history and thinking back of the internal and external approaches to the historiography of science. What was it like at the time? What were the technological capacities of the various people? Tinkle, I don't know if Tinkle's a boomer, using log tables. I think I even if I'm millennial or Gen X, I already had like a scientific calculator from elementary school. Like they already had scientific calculators, like the Texas Instrument. Or when I first took like algebra, you could get a Texas Instrument. But a lot of these things like internet or various things, technology changes quickly. And in terms of the ability to perform computations, we're going to talk about that in length, the connection between science, computation, mathematics, and logic in general. And today specifically, I'm going to talk about the philosophy of technology as an adjunct to the philosophy of science, because the philosophy of technology has two camps to it. There's the philosopher, there's the scientists who are involved in the philosophy of technology. However, the most of the people involved in the philosophy of technology are not actually scientists. And when they talk about the philosophy of technology, they're talking about the relationship of technology to social, cultural, economic factors, and not specifically the interplay between science and technology, which will be more that I'm focusing on. Industrial machines. Dennis Poppin was best known for his pioneering invention of the steam digester, the forerunner of the steam engine. The first working steam engine was patented in 1698 by the English inventor Thomas Savery as a new invention for raising of water and occasioning motion to all sorts of mill works by the impellant force of fire, which will be of great use and advantage for draining mines, surveying towns, and water, and for the working of all sorts of mills where they have not the benefit of water nor constant winds. The invention was demonstrated for the Royal Society on the 14th of June, 1699, and the machine was described by Savary in his book The Miner's Friend, or an engine to raise water by fire, 1702, in which he claimed that it could pump water out of mines. Thomas Newcomen perfected the practice of steam engine for pumping water. The Newcomen steam engine, consequently, Newcomen can be regarded as the forefather of the Industrial Revolution. Abraham Darby was the first and most famous of three generations of the Darby family who played an important role in the Industrial Revolution. He developed a method for producing high-grade iron in a blast furnace fueled by coke rather than charcoal. This was a major step forward in the production of iron as a raw material for the Industrial Revolution. And another topic that we're going to see many times is probably goes the overlay between the philosophy of science and science itself are conservation principles, and what eventually became the conservation of energy. And the conservation of energy is an overlap between a metaphysical, philosophical law and a scientific law. And it took many years, like from Newton and his conservation of force or acceleration and his three laws, to eventually the agreed upon conservation of energy, and then eventually Einstein and the conservation of mass and energy. But thermodynamics, where you had the heat equivalence of mechanical energy and then the electrical equivalence, and what exactly is mechanical energy, heat energy, and electrical energy, is actually a matter of metaphysics, not science. However, the conservation of energy and the mechanical equivalent of heat and mechanical or electrical energy is one of the single most important parts of science. And that's another topic that we're going to return to and go in depth to. If anyone watching Week in Review, we have been talking about that relentlessly for the last month. The invention of the vacuum pump paved the way for the experiments of Robert Boyle and Robert Hooke into the nature of the vacuum and the atmospheric pressure. The first such device was made by Otto van Guericke in 1654. It consisted of a piston and an air gun cylinder with flaps that could suck the air from any vessel that it was connected to. In 1657, he pumped the air out of two conjoined hemispheres and demonstrated that a team of 16 horses were incapable of pulling it apart. The air pump constructed was greatly improved by Hooke in 1658. Evangelistic Torricelli invented the mercury barometer in 1643. The motivation for the invention was to improve the suction pumps that were used to raise water out of mines. Criticism. The idea that modern science took place as a kind of revolution has been debated among historians. A weakness of the idea of a scientific revolution is the lack of systematic approach to the question of knowledge and the period comprehended between the 14th and 17th century, leading to misunderstandings of the value and role of modern authors. From this standpoint, the continuity thesis is the hypothesis that there was no radical discontinuity between the intellectual developments of the Middle Ages and the development of the Renaissance and early modern period, and has been deeply and widely documented by the works of scholars like Pierre Duhem, John Herman Randall, Alistair Crombie, and William Wallace, who proved the preexistence of a wide range of ideas used by the followers of the scientific revolution thesis to substantiate their claims. Thus, the idea of a scientific revolution following the Renaissance is, according to the continuity thesis, a myth. Another contrary view has recently proposed by Arun Bala in his Dialogy History of the Birth of Modern Science. Bala proposes that the changes involved in the scientific revolution, the mathematical realism turn, the mechanical philosophy, the atomism, the central role assigned to the sun in Copernican heliocentrism, have been seen as rooted in multicultural influences on Europe. He sees the special influences in Alhazen's physical optical theory, Chinese mechanical technologies leading to the perception of the world as a machine, the Hindu-Arabic numeral system, which carried implicitly a new mode of mathematical atomic thinking, and the heliocentric rooted in ancient Egyptian religious ideas associated with Hermeticism. Bala argues that by ignoring such multicultural impacts, we have been led to a Eurocentric concept of the scientific revolution. However, he states the makers of the revolution, Copernicus, Kepler, Galileo, Descartes, Newton, and many others, had to selectively appropriate relevant ideas, transform them, and create new auxiliary concepts in order to complete their tasks. In the ultimate analysis, even if the revolution was rooted upon a multicultural base, it is the accomplishment of Europeans in Europe. Critics note that lacking documentary evidence of transmission of specific ideas, Ball's model would remain a working hypothesis, not a conclusion. This is also something that we've discussed extensively on Week in Review. The question, is science racist? And how I always return to the Greeks and the precursor, the ancient ideas, especially when you're talking about the philosophy of science and the metaphysics, because in many ways, the metaphysics was much more clearly laid out in ancient times, and even most scientific ideas have ancient precursors. So, but the systemization of creating a method that built upon itself, once the scientific method was canonized in the Royal Society, is largely what's given us science today. A third approach takes the term Renaissance literally as a rebirth. A closer study of Greek philosophy and Greek mathematics demonstrates that nearly all the so-called revolutionary results of the so-called scientific revolution were in actuality restatements of ideas that were in many cases older than those of Aristotle, and in nearly all cases at least as old as Archimedes. Aristotle even explicitly argues against some of the ideas that were espoused during the scientific revolution, such as heliocentrism. The basic idea of the scientific method were well known to Archimedes and his contemporaries, as demonstrated in the discovery of buoyancies. Lucio Russo claims that science as a unique approach to objective knowledge was born in the Hellenistic period but was extinguished with the advent of the Roman Empire. This approach to the scientific revolution reduces it to a period of relearning classical ideas that is very much an extension of the Renaissance. This view does not deny that a change occurred, but argues that it is a reassertion of previous knowledge, a renaissance, and not the creation of new knowledge. It cites statements by Newton, Copernicus, and others in favor of the Pythagorean worldview as evidence. In more recent analysis of the scientific revolution during this period, there has been criticism of the dominance of male scientists. In the time, female scholars were not given the opportunity that a male scholar would have had, and the incorporation of women's work in the science during the time tends to be obscured. Scholars have tried to look into the participation of women in the 17th century in science, and even with science is as simple as domestic knowledge, women were making advances. With the limited history provided from texts of the period, we cannot know the extent of women's roles in the development of scientific ideas and invention. Another idea to consider is the way this period influenced even the women scientists of the period following it. Annie Jump Cannon was a 20th century astronomer who benefited from the laws and theories developed from this period. She made several advances in the century following the scientific revolution. It was an important period for the future of science, including the incorporation of women into fields using developments made. Okay, so there you have the scientific revolution. A lot of details there. A lot of that's going to become important. And in essence, we're going to have the difficulty of what exactly is science. And science is simply going to be what is produced by the method of the scientific method and a certain canonization process that has philosophical and metaphysical grounding. However, it's disputed. And we'll see also, as we talked about in the history of the scientific method, that's not even really clear what the scientific method is or the boundaries are. However, there's a process of a community, and we talk about Thomas Kuhn, and we'll go into detail into that also. So let's turn to John Locke. John Locke's extremely important, more for politics and society than science. Although he has some initial ideas and dealings, John Locke was around at the same time of the founding of the Royal Society. John Locke was a contemporary and friend with Isaac Newton, and Isaac Newton and John Locke mutually influenced each other. They were familiar with each other's work, and their works mutually influenced each other's work. So let's look here at John Locke's philosophy of science. Locke has been widely hailed for providing epistemological foundation for the experimental science of his day, articulating the new probabilistic form of knowledge appropriate to it. But while he is in important respects a devotee of the new science, there are also significant tensions in his thought. So I'm going to look at just a few segments of this, and we'll see also with Kant some of the larger metaphysical aspects I'm going to skip, and because God forbid this would be like a 1,000-part series if I covered all of it. So just reading these articles is taking forever, and I want to be somewhat thorough. So if there's a few people are interested or appreciate learning along, but I'm trying to achieve a little bit of a thoroughness, and just leaving. It's difficult to leave some of this stuff out. Like I read through it and then I highlighted it, and like God forbid I mention my dad's books, and my dad like highlights everything. Like a lot of he gave me some of his old math and science books from when he was in school, or that even my dad reads like math books in the bathroom, and like a lot of them everything is highlighted. So like what's the point of highlighting if you're going to highlight everything? But to some extent it's all important. But I'm just going to focus on a few elements here. Two features of Locke's intellectual landscape are most salient for understanding his philosophy of science. One concerning the new science methodology, and the other concerning its content. First, then, is the new methodological approach to understanding the natural world, accompanied by profound shifts in the conception of induction and scientific knowledge and its disciplinary boundaries. Locke's reaction is, for the most part, progressive, impressed by experimental methods and cognizant of their poor fit with the Aristotelian ideal. He defines a distinct kind of knowledge, one inferior to genuine scientific knowledge, but appropriate to human sensory capacities. In so doing, he develops an epistemological basis for the new experimental philosophy. Yet his reaction also has its conservative aspects, one that some see as having limited him in the face of the new science evolving methodology. He retains as an ideal the notion that scientific knowledge is demonstrative and certain, an ideal he shares with the two main targets of his essays, the speculative system of the Aristotelians and the Cartesians. The second salient feature is the dominant scientific theory of his day, the new science's corpuscular hypothesis. As defined for the purpose of this article, the corpuscular hypothesis takes observable bodies to be composed of material property particles of corpuscles, takes impulse action by surface impact to be the primary, if not the sole means of communicating motion, and attempts to reduce qualities at the level of observable bodies, such as color, to the primary, that is, inherent properties of the particles composing those observable bodies, in what may be called the orthodox version. The corpuscular hypothesis restricts those inherent properties to size, shape, number, and motion, and holds that all other qualities and operations are explicable in terms that restricted sets of property. The orthodox version thus implies a proviso of contact action, that bodies causally interact only locally by impact, such that unmediated action at a distance is denied. Plenist and atomist versions of the corpuscular hypothesis may be distinguished. Plenist theories deny the void and assert a plenum of matter, as Descartes does by identifying matter with extension. Such theorists may speak of particles, but their particles are not atoms, being infinitely or at least indefinitely divisible. Atomist theories, by contrast, accept the void and take the particles of corpuscles comprising compound bodies to be indivisible, or at least probably so. Since Locke's sympathies are clearly with the atomist version, the term corpuscular hypothesis shall refer to that version throughout this article, unless indication is given otherwise. So this part gets extremely complicated, and there's a lot here, and Kant deals extensively with this also in terms of what is mostly Newtonian's three laws, even going back to Galileo. What is an object? What is motion? How is motion transferred? And philosophically and metaphysically, these things are extremely difficult to define. So to say that duvet is a unique object that has a mass, a position, a shape, exist in time, could be understood scientifically, but philosophically, these things are all questionable. To so say one object, this cup and the computer or any of the books on my shelf or any individual object to define them as a separate object and then say, what does it mean, the interaction and the laws, the transferring of uh, momentum, impulse, force, acceleration, um, so to say, is the realm of metaphysics. And largely these questions are unanswered today. And, I'm going to pivot back to this when we get into other theories that give alternative explanations, such as um, like the holographic universe, uh, Einsteinian understandings like Hilbert space of the connection between space and time, non-Euclidean geometry, uh, even eliminativism to state that the material realm is an illusion, illusionism, and all these various things, because the metaphysics is extremely problematic. And so the early philosophers, Leibniz, Descartes, Newton, Locke, through Kant, basically all focus on these difficult metaphysical questions. However, eventually, largely the scientific method just accepts that we don't know the answers to these questions, but we could accurately describe and predict and calculate and make equations that describe and predict, explain phenomenon. And so science as the method has went on somewhat dismissive. And we're going to see here that one of the key things is the divorce between metaphysics and science here. But a lot of the stuff that Locke gets involved with is to the modern eyes, it's almost, unless you're trained in metaphysics, and these days, like, really no one's trained in metaphysics. Like, as I mentioned, there's a handful of people who study philosophy of science, very small, like relatively, um, probably for like every 1 out of 100 people who study science is someone who studies the philosophy of science, maybe even less. And the majority of the people who study the philosophy of science have a theological bent and therefore are somewhat at odds with science itself. So the philosophy of science many times is full of people, metaphysicians from religious, theological, spiritual frameworks that are actually at odds with science. But going through John Locke and later Kant, and especially Kant, I'm going to go through Kant in more detail, who's probably more important than Locke in terms of the science. But a lot of this metaphysical stuff is extremely complicated, and if you don't have a background in metaphysics, may be near impossible. But hopefully, be a tool to jump in, and through seeing this, the philosophy of science, hopefully, will be an interesting subject. Duvid's a philosopher of science. Duvid's a metaphysician, and hopefully, Duvid will spark the interest of metaphysics into others through doing these streams. Locke on knowledge and natural philosophy, science, and human knowledge. Locke's great epistemological contribution to philosophy is a conception of human knowledge suitable for the experimental science of his day, one that is natural philosophy, at least, will replace the old Aristotelian concept. According to the Aristotelian conception, scientific knowledge is certain knowledge of necessary truths, which can, in principle, be expressed in syllogistic form, the conclusion following from the self-evident premises. In the domain of natural philosophy, it is certain knowledge of real essences. The concepts of science plays an important role in the development, Locke's development of his conception of the probabilistic sort of knowledge that is possible for humans in the domain of natural philosophy. He used it as a foil when explaining why humans must settle for probabilistic knowledge, their science remaining always out of reach. Here, sentia, the Latin sentia, can serve as the foil because it is attainable for human beings in certain domains. However, Locke thinks that for noble or spirits such as angels, it is also attainable within natural philosophy. Historical roots of scientia. The concept of genuine scientific knowledge that Locke inherits and in some manner retains, scientia has its roots in Aristotle, as it's set out in Book 1, Section 2 of Posterior Analytics. For Aristotle, only necessary truths are the objects of scientific knowledge, and since scientific knowledge requires knowledge of causes, it also requires knowing the fact is necessary by knowing its necessary relations to its causes. Among Aristotle's manifold causes, the main one in question here is the formal cause, the nature of essence. The knower's epistemic stance towards the necessary truth and its relation to causes is one of certainty, and the certain fact is demonstrable via a syllogism, specifically one in which the premises are self-evident, requiring no demonstrations themselves. The stipulation of the premises of a scientific demonstration must be indemonstrable, that is, self-evident, lead to a prima facie difficulty. This conception of scientific knowledge is intended to encompass not only conceptual propositions, but also propositions about the real natures of essences and substances, which are to say, propositions about the world. As with any other demonstration, a demonstration in natural philosophy must have premises that are self-evident, since otherwise a regress would ensue. Yet it is not clear, at least from a contemporary perspective, how the premises can be self-evident, since they must be experience-based. Now, it would be overstating matters to say that the problem appears only from a contemporary perspective. There was some recognition of it in the ancient and medieval periods. Still, before the advent of the experimental science, the problem was not strongly felt because experience was understood in a different way. For one thing, the notion of an experiment, an artificially constructed single event, or a series of events designed to test for a predicted outcome did not exist. Moreover, among the scholastics, Aristotelians, a single naturally occurring event could not by itself be regarded as revealing of natural processes because it might be a monster. It might be an event that went against nature rather than being produced by and thus revealing of nature. Events as generally experienced, however, were regarded as being revealing of nature, and so they could provide the universal truths needed as premises in the syllogism. Yet for the most part, natural philosophy stands side by side with the conceptual disciplines, even into the modern period. Bacon, though associated with induction, accepts the demonstrative conception of scientific knowledge, as does Galileo, who uses experiments to reveal fundamental principles. As empirical methods are refined and more widely accepted, the belief in natural philosophy can stand under the umbrella of scientia, comes under increasing pressure. Some thinkers resist the pressure, most notably Descartes, who derives his laws of nature by a priori reflection upon God's nature and placing confidence in these rationalist methods, denying that his third law of nature is undetermined by conflicting observations of colliding bodies. Yet for the experimentalists themselves, including Locke's mentor Boyle, observations and experiments are the primal vehicles to knowledge. It should be noted, however, that most advocates of experimentalism did not consider speculation wholly illegitimate, instead insisting that it be delayed until considerable experimental and observational evidence has been amassed. And we'll see also that cause and effect are also questionable, the relation of cause and effect to science and the scientific method. And cause and effect is more metaphysics and philosophy than science. And do scientific laws such as Newton's equations, the modern mathematical conception of physical laws actually convey cause and effect? And what is Aristotle's syllogism, or Aristotle's understanding of scientific knowledge, as understanding the true relationship between cause and effect that was more determined by contemplation and observation than experiment, as where the scientific method is fundamentally geared towards experiment, although also requires observation and thought. However, experiment is the main factor. Scientia and natural philosophy, obstacles to human attainment. Scientia serves as the backdrop against which Locke develops the conception of the knowledge that is possible in natural philosophy for human beings. Having retained the idea of scientia as exemplified by geometry, yet having also absorbed the import of Boyle's experimental method, Locke is driven to his characteristic pessimism about the kind and extent of knowledge possible for us in natural philosophy. The meanest and most obvious things that come in our way have dark sides that the quickest sight cannot penetrate into. Due to the weakness of our faculties, Locke suspects natural philosophy is not capable of being made a science. And we'll see earlier, like the term has said, scientist comes from Whewell in the early uh, 1800s. And originally, you had science was generally called natural philosophy. And so we'll see this in the Lockean period of and even through Kant, this wrestling with the question, what is science? Is it a natural philosophy? Is it its own thing? And then science itself as a field is just the word knowledge. And largely today, science means the product of the scientific knowledge, which is divorced from philosophy and metaphysics. So these Lockean precursors are extremely important. Scientia in general. Locke takes knowledge generally to consist in the perception of the connection and agreement or disagreement and repugnancy of any of our ideas. And among the three kinds of knowledge that he distinguishes, intuitive, demonstrative, and sensitive, the former two are kinds of certain knowledge. Intuitive and demonstrated knowledge differ from in the number of intuitions involved and consequently differ in their degree of certainty. Intuitive knowledge is the most certain because the truth is grasped immediately. There are no intermediate steps, and doubt is impossible because the mind can no more avoid recognizing the truth than the open functioning eye could avoid seeing light when turned towards the sun. Demonstrative knowledge, though also qualifying as certain, is less so because it involves intermediary steps. We cannot grasp immediately that the three angles of any triangle are equal to two right triangles and must instead construct the steps of a proof. Upon doing so, and upon grasping the connections between the steps of a proof, we have demonstrated knowledge. Intuitive and demonstrated knowledge are forms of scientia. To understand Locke's notion of scientia, we must consider its objects' real essences and the necessary connections that flow from them. Denying the Aristotelian view that a single essence both grounds the properties of a thing, making it what it is, and provides the basis for classifying it, Locke draws a distinction between real and nominal essences, whereas the nominal essences consist in the set of observable qualities we use to classify a thing, which implies the nominal essence could vary across time and communities. The real essence or real or internal constitution, as Locke sometimes writes, is that which makes a thing what it is. Essence may be taken for the being of anything, whereby it is what it is, and thus the real internal but generally in substances known constitution of things whereon their discoverable qualities depend may be called their essence. This is the proper original signification of the word as is evident in the formation of it, essentia, in its primary notation signifying properly being. And in this sense, it is still used when we speak of the essence of particular things without giving them any name. According to another interpretation, the real nominal essence distinction is metaphysical and thus more fundamental than the primary secondary quality distinction, which is a physical distinction belonging as it does to a particular physical theory, the corpuscular hypothesis. We have scientific knowledge of something when we know its real essence, and since its qualities flow from the real essence, when we know the necessary connections between the essence and its other qualities, geometry serves as an exemplar, as it did for so many of Locke's predecessors. In knowing what a triangle is, we can conceive that things being otherwise than that sum of its three angles equals the sum of two right angles. Scientia is possible in another conceptual domain also, morality. Morality is characterized by discernible necessary connections, as Locke is adamant that we can have the same level of certainty there is in geometry. And that applies to the truth claims, that Locke would be of the opinion that the truth claims of morality are equivalent to the truth claims of Okay, God forbid. Apologize about that. Looks like my stream. Okay, God forbid. Apologize about that. It looks like my stream temporarily went down. I've been having internet connections. Okay, sorry about that. God forbid. I've been having internet problems today, and so I apologize about that. God forbid my stream went down, um, and my internet's been flicking in and out. Sorry about that. So thanks for tuning in. Thanks for sticking with this. So I'm on section 2.3. So um, you can't see my highlights, so you've seen the link. So I'm going to continue reading from where I was. So I greatly apologize about that. And my internet's been flicking in and out today. And so let me just continue about that. Thanks for pointing it out in the chat that there was a problem. Okay. So Locke predates science, and we're talking about natural philosophy, where Isaac Newton, Leibniz, originally science was largely part of natural philosophy, describing the material realm, and eventually science, just the word from knowledge, becomes divorced from philosophy and its own thing. And so here Locke is talking about the precursors, and he's saying he's a spiritualist. He's still a dualist who believes in God. And he's talking about truth being unattainable, the claim that there is a truth. However, man can't actually know the truth. Man could only know probability of some things being more likely than others. And so Locke is looking into science and the early scientific method as a form of getting closer to the truth that we're going to see later when I get into Kant, and especially the Neo-Kantians in the Marburg School, that will take upon this Lockean scientific concept of probabilistic truth, which Duvid's multiple truth hypothesis could also be considered Lockean in nature, in the sense of a probabilistic view towards truth is the best that we could do. So, human knowledge and natural philosophy, sensitive knowledge. The conclusion that no intuitive or demonstrative knowledge of substance is possible for us, their real essences and necessary connections being out of reach, places Locke at a crossroads. One path is skepticism, the view that without certainty, no knowledge of substance is possible at all. He rejects that path, denying that hyperbolic doubt could be genuine for either the self or for external objects. The other path, the one he follows, involves lowering the bar for admitting a third kind of knowledge, one that lacks certainty, sensitive knowledge. Sensitive knowledge is knowledge of the effects that come every day within the notice of our senses without an understanding of their causes. We must be content to be ignorant of those causes instead of knowing real essences, the causal basis of the properties we perceive. We know only those perceived properties from which we construct nominal essences. Instead of employing deduction, we are forced to rely upon trials, observation, and induction, instead of knowing the necessary connection holding between a substance's real essence and its other qualities, including its tertiary qualities. We know only of the coexistence of properties, and from the mere regular coexistence of properties found in observed cases, Locke observes we could not know with certainty that the same set will be found coexisting in the next case. Yet our discoveries about coexistence of properties, though they are merely contingent particulars of, or insofar as they are applied beyond the particular cases we have actually observed, are merely probable, can yet qualify as real knowledge. To do so, our ideas must meet certain conditions. The complex idea that we refer to a substance must comprise all and only those simple ideas that we have found to coexist in nature. Here Locke is concerned to show that sensitive knowledge deserves its appellation since it can be distinguished from arbitrary or otherwise poorly grounded claims. Sensitive knowledge is far less than scientia, but far more than ungrounded opinion. As for general claims about substance based upon observed particular matters of fact, these two can qualify as real knowledge. So I'm going to skip some of these tensions and debates within Locke's time. There are some important precursors in Locke, and that's why I'm covering it. And so I'm going to cover a little bit about the relationship between Isaac Newton and John Locke. So yeah, thanks Tinkle, Conway, and Nam. Conway, thanks for informing me in the chat. It was down, so I could fix that. And thanks for sticking through this. So Locke and Newton. Locke and Newton probably first met in 1689. So epistemology and methodology. A great deal of resemblance to Locke's epistemological approach can be seen in Newton, who holds that revelation apart, we must gather what knowledge we can from our perceptions, and anything like a real essence eludes us. In the early manuscripts, for instance, Newton denies knowing the essential and metaphysical constitution of matter. We certainly do not know what is the substance of any things. We see only the shapes and colors of bodies. We hear only their sounds. We touch only their external surfaces, but there is no direct sense, and there are no indirect reflected actions by which we know innermost substances. Locke and Newton also share the problem of an evidentiary deficit insofar as they subscribe to corpuscularianism. Thinkers who did subscribe tended to rely on transduction, also called transdiction, as inductive inference that is empirical insofar as it relies upon observed cases, but which generalizes not only to unobserved cases, but to ones that are unobservable. Perhaps Locke categorized Newton's epistemological achievement in natural philosophy as a contribution to sensitive knowledge alone. That is, perhaps he saw Newton's mighty design in advancing the science, also confined to providing a firm basis for natural philosophy through his experimental method. But did he perhaps instead take Newton's mathematical methods as an offering that demonstrations needed to push natural philosophy into the domain of demonstrative knowledge and hence scientia? Ontology. Locke and Newton accept similar ontologies, although both, quite independently of one another, are characteristically circumspect about the nature of mind. They may be considered substance dualists. Newton, though indicating in the early manuscript that he does not pretend to know the substantial foundation of minds, consistently presents God and minds as immaterial, lacking certain characteristics of body, namely hardness, impenetrability, and resistance. Similarly, Locke, though he explicitly allows the possibility of thinking matter in his essay and discusses it at length with Stillingfleet, emphasizes that in all probability the soul is immaterial, but while Newton takes even immaterial spirits to be spatially extended, such that a mind can co-occupy place with the body and God with all bodies, it is not clear that Locke agrees. As for the concept of body, their views are again similar without being identical. Both confront the problem of a substratum or substance in general, one that Locke notoriously finds vexing. Newton dispenses with the problem more easily. He eliminates the unintelligible notion of prime matter by associating perceiving properties with determined regions of extension. Both also attack Descartes' identification of matter with extension, instead defending the void and showing strong sympathy for atomism. Okay, so there you have it with a little bit of John Locke. And, we can review, I've went in depth into concepts of Descartes and Descartes' dualism. So a lot of people say, okay, so Galileo runs into problems with the church for making claims that were contrary to doctrine. So Descartes, who was also a Catholic and presumably saw the difficulty that Galileo had, ends hylomorphism and starts substance dualism. So you had ancient Greek dualism of hylomorphism, form and matter, and through Descartes' kind of form of extension tries to unify form and matter into the material realm and then separate soul and mind into a separate realm. And by doing that, Descartes saves himself with trouble with the church in saying that the realm of the mind is the realm of the church and theology and philosophy, that science, material science, has nothing to say about it. So Newton and Locke generally took upon that same epistemology, the metaphysics, that they were purely talking about material things, and they had their, at least science had nothing to say upon mind, and that, the Galilean mind independence of scientific laws. And then even questions about what is the nature of matter and the metaphysical questions that Newton almost wholly avoids. Locke tries to deal with them more than Newton does and delves a little bit more into. And we'll see that Kant goes more into these metaphysical questions of what is going on. But you start to see the separation of science from metaphysics, and that becomes important to where metaphysical claims have no bearing on scientific claims, at least from a period, and there might be a pushback in modern times to unify metaphysics and science. But you begin the divorce of metaphysics and science, and you'll see over the development of science and the crystallizing of the scientific method, there's almost a complete divorce between metaphysics and what will become known as science. So I have quite a few more things to do here. So let me jump into, I was going to do the scientific method. That one's a little bit longer. So let me do first here. Scientific representation, which is going to be a little bit on this conception of a model of what exactly do scientific theories represent. And Samish, thanks for tuning in. I'm not sure if you asked a question, what exactly, so if your question, what is science exactly, that it's unclear. Like, so the question of what is science is a question for philosophy and metaphysics. And I mentioned almost no scientists are metaphysicians or philosophy. Most scientists are just scientists, and that means that they're within the scientific method. And when I get to Kant, like, so Samish, who is what they might call a social scientist, and that also comes to the question of what is social science? Why is it important that social sciences is scientific? And largely that means following the scientific method. And so I'm going to go in detail. I'm going to go through the whole Wikipedia on the scientific method, and I'm going to go much more into, like, if I continue the series, it's almost endless, all these conceptions within the scientific method. So the multiple truth hypothesis is really a metaphysical framework for evaluating truth claims. So right now, I'm grounding. I'm going to separate a boundary of science to say what are the truth claims that are claimed by science, and the fine line, because truth is, I would say, more universal than science. Science is a subcategory of metaphysics. From my conception of metaphysics and philosophy, because science only deals with a certain methodology for material phenomenon. And so you would have a truth level to scientific claims, and you have a truth level to other claims. And so the multiple truth hypothesis is a metaphysical methodology for dealing with multiple conflicting models, truth claims, and evaluating. Like, so I was covering John Locke, and so John Locke had the conception of, Duvid in the multiple truth hypothesis, probably Lockean in that terms, that we can't actually know truth. That possibly there's a truth. If there is a truth, it's connected to, like, theology and God. But from the man's eye perspective, we could only know truth probabilistically, that certain things are more probable than others, and we might even be able to define those probabilities to say how much probable some things are than others without actually defining them as truth. So that's the multiple truth hypothesis, is a working system for multiple conflicting theories and evaluating ideas, concepts, phenomenons, models through multiple lenses that would give different truth conceptions. So I went last stream on stream 1 into Kuhn's scientific revolutions. So here I'm going to cover now, before I go in depth into the scientific method, scientific representation. And there's actually a lot to do with what is a model. And so scientific representation is an overlap to model theory. And so to say, science is a model of something. And saying, well, it's a model of reality, it's a model of an explanation of a perceived phenomenon, and the perceived phenomenon, how well the model fits reality, is we'll call the truth level. So like if there was a 1 value, if the model perfectly represents reality, then you could call it true. If a model has explanatory power to reality, but does not perfectly represent it, it just has a truth value, a probabilistic value, and other competitive models might explain certain phenomenon better, like the Kuhnian interpretation. So that's where multiple truth hypothesis is. I don't even know how to frame it, so that's why I'm just reading all these various things, because I think multiple truth hypothesis is more in the science of the philosophy of science than science itself. So multiple truth hypothesis is not a scientific theory per se. It's a theory of the philosophy of science. And the philosophy of science itself is not scientific, it's philosophical. And as I said, most scientists are not philosophers of scientists. Most scientists themselves don't actually study the philosophy of science. The majority of people who study the philosophy of science are actually non-scientists. So with that, let's jump right in. And so we're going to look at scientific representation, which is an overlay to model theory. I'm going to get more into what we call scientific models, and you'll see there's a lot of overlap, and there's some important theories here. Scientific representation. Science provides us with representations of atoms, elementary particles, polymers, populations, pandemics, economies, rational decisions, airplanes, earthquakes, forest fires, irrigation systems, and the world's climate. It's through these representations that we learn about the world. This entry explores various different accounts of scientific representation, with a particular focus on how scientific models represent their target systems. As philosophers of science are increasingly acknowledging the importance, if not the primacy, of scientific models as representational units of science, it is important to stress how they represent plays a fundamental role in how we are to answer other questions in the philosophy of science. And so this is a long entry. I'm just going to read sections of it. Problems concerning scientific representation. In most general terms, any representation that is the product of a scientific endeavor is a scientific representation. Different authors frame the problem of scientific representation in different ways, and eventually they examine different issues. So a discussion of scientific representation has to begin with a clarification of the problem itself. Reviewing the literature of the subject leads us to a conclusion that there is no such thing as the problem of scientific representation. In fact, there is at least 5 different problems concerning scientific representation. A number of contributors to the debate have emphasized that scientific representation is an intentional concept depending on factors such as a user's intentions, purposes, and objectives, contextual standards of accuracy, intended audience, and community practices. A first important condition of adequacy on any reply to this problem is that scientific representations allow us to form a hypothesis about their target system. Every acceptable theory of scientific representation has to account for how reasoning conducted on representations can yield claims about their target system. Sawyer, 1991, refers to this kind of representational-based thinking as surrogative reasoning, and so we call this the surrogative reasoning condition. This condition distinguishes models from lexicographical and indexical representations, which do not allow for surrogative reason. Representations other than scientific representations also allow for surrogative reasoning, which raises the question, how do scientific representations differ from other kinds of representations that allow for surrogative reasoning? Callender and Coyne point out that this is a version Popper's demarcation problem, now phrased in terms of representation, and so we refer to as the representational demarcation problem. Callender and Coyne voiced skepticism about there being a solution to this problem and suggest the distinction between scientific and non-scientific representation is circumstantial. Scientific representations are representations that are used or developed by someone who is a scientist. Those who reject the notion that there is an essential difference between scientific and non-scientific representations. Some representations are accurate, others aren't. However, both are representations, whether accurate or not. The quantum mechanical model is an accurate representation of the atom, at least by our current lights, but the Thomson model isn't. On what grounds do we make such judgment? Morrison, 2008, reminds us that it is a task for the theory of representation to identify what constitutes an accurate representation. We call this the problem of standards of accuracy. Providing such standards is one of the issues an account of representation has to address, which, however, is not to say that accurate representation is the sole epistemic virtue of scientific models. There are numerous considerations to take into account when evaluating a model's adequacy for its purpose. A related condition concerning models that misrepresent, in this sense that they lack target systems, models of the ether, phlogiston, four-sex populations, and so on, all deemed scientific models, but ether, phlogiston, four-sex populations don't exist. Such models lack actual target systems, and one hopes that an account of scientific representation would allow us to understand how these models work. This need not imply the claim that there are representations in the same sense as models with actual targets, and we will discuss below there are accounts that deny targetless models the status of being representation. A further condition of adequacy for an account of scientific representation is that it must account for the directionality of representation. Representations are about their targets, but at least in general, targets are not about their representations. There is an essential directionability to representations, and an account for scientific or epistemic representations has to identify the root of this directionality we call the requirement of directionality. Some representations, in particular models and theories, are mathematized, and their mathematical aspect are crucial to their cognitive and representational function. This forces us to reconsider a time-honored philosophical puzzle, the applicability of mathematics in the empirical science. The problem can be traced back to Plato's Timaeus. The question how a mathematicized model represents its target implies the question of how mathematics applies to a physical system. For this reason, our fifth and final condition of the adequacy of the account of representation has to explain how mathematics is applied to the physical world. We call this the applicability of mathematics condition. In answering the above questions, one is invariable runs up against the further problem, the problem of ontology. What kinds of objects are representations? The Newtonian model of the solar system, the Locke Volterra model of predator-prey interaction, and the general theory of relativity are not things you can put in your laboratory table and look at it. The problem of ontology is to come clear on our commitments and provide a list of things which we recognize or don't recognize as entities performing a representational function, and give an account of what they are in case these entities raise questions. What exactly do we mean by something that one holds in one head rather than one's hands? In sum, a theory of scientific representation has to respond to the following issues. 1. Address the representational demarcation problem, the question how scientific representations differ from other kinds of representation. 2. Those who demarcate scientific from non-scientific representations have to provide an answer to the scientific representation problem. Fill in the blank. S is a scientific representation of T if and only if. Those who reject the representational demarcation problem can address the epistemic representation problem. Fill in the blank of the epistemic representation scheme. S is an epistemic representation of T if and only if. Respond to the problem of style. What styles are there and how can they be characterized? 4, formulate standards of accuracy. How to identify what constitutes an accurate representation. 5, address the problem of ontology. What are the kinds of objects that serve as representations? Any satisfactory answer to these 5 issues will have to meet the following 5 conditions of adequacy. Surrogative reasoning. Scientific representations allow us to generate hypotheses about their target systems. Possibility of misrepresentation. If S does not accurately represent T, then it is a misrepresentation, but not a non-representation. S means a scientific representation, and T is the target. Targetless models. What are we to make of scientific representation that lacks targets? Requirement of directionality. Scientific representations are about the targets, but targets are not about their representations. Applicability of mathematics. How does the mathematical apparatus used in some scientific representations latch onto the physical world? Listing the problems in this way is not to say that there are separable and unrelated issues. This division is analytical, not factual. It serves to structure the discussion and to assess proposals. It does not imply that an answer to one of these questions can be disassociated from what stance we take on the other issues. Any attempt to tackle these questions faces an immediate methodological problem. As per the problem of style, there are different kinds of representations, scientific models, theories, measurement outcomes, images, graphs, diagrams, linguistic assertions are all scientific representations, and even within these groups there can be considerable variations, but every analysis has to start somewhere. So the problem is where? One might adopt a universalist position, holding that the diversity of style dissolves under analysis, and at bottom, all instances of scientific epistemic representation function in the same way and are covered by the same overarching account. For such a universalist, the problem loses its teeth because any starting point will lead to the same result. Those of particularist bent deny that there is such a theory. They will first divide the scientific epistemic representations into relevant subclasses and then analyze each subclass separately. Different authors assume different stances in this debate. Okay, yeah, so if Samish is still watching, this is where the multiple truth hypothesis comes into play. Multiple truth hypothesis would more be what mathematically is called model theory. And your model theory is generally considered mathematical or logical, to say a model is a logical representation. So what I'm talking about right here, scientific representation, is probably considered the philosophy of science, but some also would consider it logic. And you'll see, like, even within this, it's going to become logical notation. And as I move forward and get more advanced, a lot of this is just going to become pure logical notation and representation for how do you reduce a model to mathematical logical representation, and then how do you evaluate the truth claim, the truth value of a various model, and how do you compare multiple models that have various truth values, and they might have various truth values upon the target. So you can see a common thing here. You have the scientific representation, the model, and then the target of what's trying to be modeled. And you might have a given target that one model accurately represents, but doesn't accurately represent other models. And how do you assess a truth value? So this would be more where multiple truth hypothesis is going to come into play. General Grecianism and stipulative fiat. Callender and Cohen give a radical answer to the demarcation problem. There is no difference between scientific representation and other kinds of representation, not even between scientific and artistic representation. Underlying this claim is a position they call general Grecianism. The core of general Grecianism, GG, is the reductive claim that all representations owe their status as representations to a privileged core of fundamental representations. So the stipulative fiat, a scientific model M represents a target T if and only if a model user stipulates that M represents T. The The first problem facing stipulative fiat is whether or not stipulation or the bare intentions of language users suffice to establish representational relationship. In the philosophy of language, this gets called the Humpty Dumpty problem. That so say a model M represents a target if the person says so. So it doesn't necessarily have to be true to be a model. So say I have a model to explain this, and even if it's inaccurate, it doesn't change the fact that I have a model to explain this. And that's the furthest, the Grecian, the GG understanding, where a piece of art or literature is also considered a representation, and that there is no clear delineation between science and non-science. That science is a model representation of a target in the same way that art is, and it's actually impossible to delineate the clear dividing line between artistic representation and a scientific representation. The similarity conception. Similarity and representation initially appear to be two closely related concepts, and invoking the former to ground the latter has philosophical lineage stretching back to at least as far as Plato's Republic. In its most basic guise, the similarity conception of scientific representation asserts that scientific models represent their targets in virtue of being similar to them. This conception has universal aspirations in that it take into account for representation across a broad range of different domains. Accuracy, style, and ontology. The fact that relevant properties can be delineated in different ways could potentially provide an answer to the problem of style. If M representing T, if the model representing the target involves the claim that M and T are similar in a certain respect, the respect chosen specifies the style in the representation. And if M and T are in fact similar in that respect, and to the specified degree, then M accurately represents T within that style. For example, if the model and target are proposed to be similar with respect to their causal structure, then we might have a style of causal modeling. If the model and the target are proposed to be similar with respect to structural properties, then we might have a style of structural modeling, and so on and so forth. A first step in the direction of such an understanding of styles is the explicit analysis of the notion of similarity. The standard way of cashing out of what it means for an object to be similar to another object is to require that they co-instantiate properties. The geometric account associated with Shepard 1980 assigns objects a place in a multidimensional space based on values assigned to their properties. This space is then equipped with a metric, and the degree of similarity-dissimilarity between two objects is the distance between the points representing the two objects in that space. This account is based on the strong assumptions that values can be assigned to all features relevant to similarity judgments, which is deemed unrealistic, and to the best of our knowledge, no one has developed such an account in the context of scientific representation. Two objects are alike to the extent that they co-instantiate similar properties. Two objects are partially identical to the extent that they co-instantiate identical properties. The notion of sharing features should be analyzed in a pluralistic manner. Sharing a feature sometimes means sharing the exact same feature. Sometimes it means to share features which are sufficiently quantitatively close to one another, and sometimes it means having features which are themselves sufficiently similar. A further question that remains for someone who uses the notion of similarity to answer to the problem of style and provide standards of accuracy in the manner under consideration here is whether it truly captures all of the scientific practice. Similarity theorists are committed to the claim that whenever a scientific model represents its target system, that is established in virtue of the model using specifying a relevant similarity, and if the similarity holds, then the representational relationship is accurate. Another problem facing similarity-based approach concerns their treatment of the ontology of models. If models are supposed to be similar to their targets in the ways specified by theoretical hypothesis, then they must be the kind of things that can be so similar. Many interested scientific models are not like this. This is what hacking aptly describes as something you hold in your head rather than your hands. We call such models non-concrete models. The question then is how such models can be similar to their targets. At very least, these models are abstract in the sense that they have no spatial temporal location, but if so, then it remains unclear how they can instantiate the sort of properties specified by theoretical hypothesis, since these properties are typically physical and presumably being located in space and time is necessary condition for instantiating such properties. The structuralist conception of model representation originated in the so-called semantic view of theories that came to prominence in the second half of the 20th century. The semantic view was originally proposed as an account of the theory structure rather than scientific representation. The driving idea behind the proposition is that scientific theories are best thought of collections of models. This invites the question, what are these models and how do they represent their target system? Most defenders of the semantic view of theories take models to be structures which represents their target systems in virtue of there being some kind of morphism between the two. The conception has two prima facie advantages. The first advantage is that it offers a straightforward answer to the epistemic representation problem and the scientific representation problem if the focus is on scientific representation. And one of the accounts for surrogative reasoning, the mappings between the model and the target allow scientists to convert truths found in the model into claims about the target system. The second advantage concerns the applicability of mathematics. There is a time-honored position in the philosophy of mathematics which sees mathematics as the study of structures. It is a natural move for the scientific structuralist to adopt this point of view, which then provides a neat explanation of how mathematics is used in scientific reasoning. And so this is going to become extremely applicable to mathematics as the main form of scientific representation, as mathematical models are the main form of scientific representations and models of the supposed target system, and that target would be the material realm. Structures and problems of ontology. It is important to be clear on what we mean by object and relation in this context. As regards objects, all that matters from a structuralist point of view is that there is so and so many of them. All we need are dummies and placeholders whose only property is objecthood. Similarly, when defining relations, one disregards completely what the relation is in itself. The first basic posit of the structuralist theory of representation is that models are structures in this sense. The second is that models represent their targets by being suitably morphic to them. Supps has articulated this stance clearly when he declared that the meaning of the concept of model is the same in mathematics as the empirical sciences, and many have followed suit. So we are presented with a clear answer to the problem of ontology. Models are structures. The remaining issue is what structures themselves are. Are they Platonic entities, equivalence classes, modal constructs, or yet something else? In the context of a discussion of scientific representation, one can push these questions off to the philosophy of mathematics. Structuralism and the epistemic representation problem. So it mentions here, for example, you could use anything to represent anything. So it's like, let's say that this cup represents Duvid, just for a source, like the chess piece or like a notch for counting. If I want to count something and I have anything, I could say, well, this represents whatever I'm using to count. And so it could be completely arbitrary, or your verse we're saying where we say things that products of the mind or product of the hands, where you have something like mathematics, which is even hard to describe, a metaphysical construct, something that doesn't exist, like if it's a Platonic form. So if a model is a mental construct like mathematics that doesn't have a physical representation. So these are important, extremely important issues. I'm going to come back to this many, many times. Most of these problems can be resolved by making moves similar to the ones that led to Similarity 3, introduce agents and hypothetical reasoning to the account of representation, going through the motions one finds. So structuralism 2 here, a scientific model M represents a target system T if and only if there is an agent A who uses M to represent a target system T by proposing a theoretical hypothesis specifying an isomorphism between S sub M and S sub T. So now we're getting more into what would be like model theory in the logical formulation of these laws, where a model is specific to the person. So a model of the target is specific to the agent A who used the model, and it necessitates a hypothesis and an isomorphism between S sub m and S sub t. And I forget what S was, structure, between the structure, S here are the structure. This is in line with Van Frazen's view on representation. He offers the following as the Humstats of theory of representation. There's no representation except the sense that some things are used, made, or taken to represent things as thus and so. Representation is an intentional act relating to objects. So as we get more into this in the more weeks coming forward, it will be likely to becoming more mathematical and logical representation. So the true, so this will be the philosophical, metaphysical background, and as multiple truth hypothesis advances, there will be an element that will be within a mathematical, logical formulation that will be symbolic in nature, and it comes as a model. So to say a model as a non-physical structure. Demarcation, accuracy, style, and target and structure. Structuralism's stand on the demarcation problem is by and large an open question. Unlike similarity, which has been widely discussed across different domains, structural mappings are tied closely to the formal framework of set theory and have been discussed only sparingly outside the context of mathematical sciences. The problem of styles is to identify representational styles and characterize them. A proposed structural mapping between the model and the target offers an obvious response to this challenge. One can represent a system by coming up with a model that is proposed to be appropriately morphic to it. This delivers an isomorphism style, the homomorphism style, and the partial isomorphism style, and so on. We can call these morphism styles when referring to them in general. Each of these styles offers a clear-cut condition of accuracy. The representation is accurate if the hypothesized morphism holds. It is inaccurate if it doesn't. This is a neat answer. The question is what status it has vis-a-vis to the problem of style. Are morphism styles merely a subgroup of styles, or are they privileged? The former is uncontentious. However, they emphasize many structuralists' place on structure-preserving mappings suggest that they do regard morphisms as merely one way among others to represent something. What they seem to have in mind is the stronger claim that a representation must be of that sort, or that morphism styles are the only acceptable styles. This claim seems to conflict with scientific practice in at least two respects. First, many representations are inaccurate in some way. Some models distort, deform, and twist properties of their target in ways that seem to undercut isomorphism, or indeed any of the proposed structure-preserving mappings. Some models in statistical mechanics have an infinite number of particles, and the Newtonian model of the solar system represents the sun as a perfect sphere, where in reality it's a fiery ball with no well-defined surface at all. It is best unclear how isomorphism, partial or otherwise, or homomorphism can account for these kinds of idealizations. So it seems the styles of representation other than structure-preserving mappings have to be recognized. Secondly, the structuralist view is a rational reconstruction of scientific modeling, and as such it has some distance from the actual practice. Some philosophers have worried that this distance is too large and that the view is too far removed from the actual practice of science to be able to capture what matters to the practice of modeling. Although some models used by scientists may be best thought of as a set of theoretical structures, there are many where this seems to contradict how scientists actually talk about them and reason with their models. Such models have the strange property of being concrete if real, and scientists talk about them as if they were real systems, despite the fact that they are obviously not. There remains a final problem to be addressed in the context of structural accounts of scientific representation. Target systems are physical objects, atoms, planets, populations, and rabbits, economic agents. Isomorphisms is a relation that holds between two structures, and claiming that a set theoretical structure is isomorphic to a piece of the physical world is a prima facie a category mistake. By definition, a morphism can only hold between two structures. If we are to make sense of the claim that a model is isomorphic to its target, then we have to assume that the target somehow exhibits a certain structure. But what does it mean for a target system, a part of the physical world, to possess a structure, and where is the target system, and where in the target system is the structure located? There are two prominent suggestions in the literature. The first originally suggested by Supps 1962 is that data models are the target and structures represented by models. This approach faces the question whether we should be satisfied with an account of scientific representation that precludes phenomena being represented. Van Frassen, 2008, has addressed this problem and argues for a pragmatic resolution. In the context of use, there is no pragmatic difference between representing phenomenon and data extracted from it. The alternative approach locates the target and structure in the target system itself. One version of this approach sees structures as being instantiated in target systems. This view seems to be implicit in many versions of the semantic view and is explicit held by authors arguing for structureless answers to the problem of applicability of mathematics. A more radical version simply identifies targets with structures. Tegmark, 2008. This approach is highly revisionary. So moving forward in the current state of science is going to become extremely important because relatively, like we talked with instrumentation, modern science is conducted by instruments and by data that has to be computed by computers and is beyond the computation power of man. And man simply reads and interprets the data that comes from a computer. In the question of models, and going back to Noam Chomsky in the cognitive revolution of cognitive models, where you had models of cognition in the human mind. But if you look at basically mathematical representation of physical laws, those could be considered models. And within the realm of the philosophy and metaphysics of science, it is largely disputed that we don't even understand what does it mean when we say that this mathematical law represents the physical world. And so, to a certain extent, the metaphysics and philosophers still don't have answers to these questions. But yet science pushes on through the scientific method. The inferential conception. The core idea of the inferential conception is to analyze scientific representation in terms of the inferential function of scientific models. According to Hughes, Denotation, Demonstration, Interpretation, DDI account of scientific representation, 1997, models denote their target are such that models users can perform demonstrations on them and interpret the results of such demonstrations in terms of the target. The last step is necessary because demonstrations establish results about the model itself, and in interpreting these results, the model user draws inferences about the target from the model. Deflationary inferentialism. Soares argues that we should adopt a deflationary minimalist attitude and strategy, 2004, when addressing the problem of scientific representation. The two different notions of deflationism are in operation in his account. The first is to abandon the aim of seeking necessary and sufficient conditions. Necessary conditions will be good enough. The second notion is that we should seek no deeper features to a representation than its surface features or platitudes, or that we should deny that an analysis of a concept is the kind of analysis that will shed explanatory light on our use of the concept. And last thing I'm going to cover here is the fiction view of models. A recent family of approaches analyzes models by drawing an analogy between models and literary fiction. The analogy can be used in two ways, yielding two different versions of the fiction view. The first is primarily motivated by ontological considerations rather than the question of scientific representations per se. Scientific discourse is rife with passages that appear to be descriptions of systems in a particular discipline, and the pages of textbooks and journals are filled with discussions of the properties and behaviors of those systems. Surface structures notwithstanding, no one would mistake descriptions of such systems as descriptions of an actual system. We know very well that there are no such systems. Thomas Jones, 2010, refers to such a description as a description of a missing system. These descriptions are embedded in what he calls the face value practice, the practice of talking and thinking about these systems as if they were real. The face value practice raises a number of questions. What account should be given to these descriptions, and what sort of objects, if any, do they describe? Are we putting forward truth-valuable claims when putting forward descriptions of missing systems? The fiction view of models provides an answer. Models are akin to places and characters in literary fiction, and claims about them are true or false in the same way in which claims about these places and characters are true and false. The second version of the fiction view explicitly focuses on representation. Most theories of representation we have encountered so far posit that there are model systems and construe scientific representation as a relation between two entities, the model system and the target system. Toon calls this the indirect view of representation, 2012. This view contrasts with what Toon and Levy call a direct view of representation. This view does not recognize model systems, instead aims to explain representation as a form of direct description. On this view, models provide an imaginative description of real things. So this is a complex topic, and I was going to read some of this stuff on Week in Review, and it was actually part of what spawned me to do this separate stream was, Week in Review not being a proper venue to just read long scientific articles. So, anyone listening or gaining from this, I'm glad you are. And that was partially the purpose in me creating these public study sessions on my own channel. Linguist is like chemist, biologist, and from this conception like physicist of what we call the natural sciences. And if you mean a linguist is someone that applies the scientific method to language. And so Noam Chomsky was claiming that, was saying he's not a linguist, meaning that he's not using the scientific method, or he's not a scientist. I mean, it's unclear. Chomsky said a lot of things and sometimes contradicts himself. Obviously, he wrote hundreds of books and he's still around. Okay, so I went in a little bit in some of the later material. So this is the last of the kind of the precursor basic material I wanted to cover, just so I had a very clear, good understanding of the basics of these various complicated processes that we refer to as science and the scientific method. And so generally when I say what is science, science is the product of the scientific method, and it's divorced from philosophy and metaphysics. And the question of what is science is the question actually of philosophy. So scientists kind of do science even though they don't know what it is. So what exactly is the scientific method is actually a matter of dispute. We covered in the history. There's no concise definition, although there's elements of it and it's somewhat well understood, the process, and people like, well, peer review, predictions, and all the various elements of, are you published? Was it peer reviewed? Is it testable? Like Popper, is it falsifiable? So I'm going to read through the vast majority of this stuff on Wikipedia just to put out there from my own head, anybody listening along that's benefiting from it, all the details of the scientific method. Wikipedia kind of more crowdsourced, Plato more in-depth and intellectual and scholarly, but from the crowdsourced Wikipedia, I'm going to put out there the full overview of the scientific method. Chomsky is an interesting character, and we might eventually get to linguistics. And I plan on actually writing an essay and covering in depth the cognitive revolution. So this precursor of what is science, the history of science, the scientific method, the philosophy of science is going to be necessary for me to return to my philosophy of mind, the science of consciousness, and Chomsky and the cognitive revolution, because in many ways, Chomsky is the father of linguistics. So he's not traditional linguistics, but he's the father of linguistics. And then he kind of got outed from his own field, that, he almost created the field and then he got outed from the field that he created, due to various factors that is too much to discuss for today. Okay, so the scientific method. The scientific method is an empirical method for acquiring knowledge that has characterized the development of science since at least the 17th century. It involves careful observation, applying rigorous skepticism about what is observed, given that cognitive assumptions can distort in how one interprets the observation. It involves formulating hypotheses via induction based on such observations, the testability of hypothesis, experimental and the measurement-based statistical testing of deductions drawn from the hypothesis, and the refinement or elimination of the hypothesis based on the experimental findings. The process in the scientific method involves making conjectures, hypothetical explanations, deriving predictions from the hypothesis as logical consequences, and then carrying out experiments or empirical observations based on those predictions. Hypothesis is a conjecture based on knowledge obtained while seeking answers to these questions. The hypothesis might be very specific or it might be broad. Scientists then test hypotheses by conducting experiments or studies. The scientific hypothesis must be falsifiable, implying that it's possible to identify a possible outcome of an experiment or observation that conflicts with predictions deduced from the hypothesis. Otherwise, the hypothesis cannot be used meaningfully tested. The purpose of an experiment is to determine whether observations agree with or conflict with the expectations deduced from a hypothesis. Experiments can take place anywhere from a garage to a remote mountaintop to CERN's Large Hadron Collider. Though the scientific method is often presented as a fixed sequence of steps, it represents rather a set of general principles. Not all the steps take place in every scientific inquiry, nor to the same degree, and they're not always in the same order. So on part one, I covered the whole part of the history of the scientific method. And as I just read about model theory, so that's something that's hardly covered here in the Wikipedia. And as I get more in depth, we'll be talking quite a bit about model theory and representation and the overlyings with the mathematical and logical advancements in Hilbert that we talked about, like Hilbert's sixth question on the axiomatization of physics and various things that will be topics for future discussions that have been, for regular watchers of Week in Review, have been regular topics the last few months. The scientific method is the process by which science is carried out. As in other areas of inquiry, science through the scientific method can build on previous knowledge and develop a more sophisticated understanding of the topics of study over time. This model can be seen to underlie the scientific revolution. Process. The overall process involves making conjectures, hypotheses, deriving predictions from them as logical consequences, and then carrying out experiments based on those predictions to determine whether the original conjecture was correct. Formulation of a question. The question can refer to the explanation of a specific observation, as in why is the sky blue, but can also be open-ended, as in how I designed a drug. The stage frequently involves finding and evaluating evidence from previous experiments, personal scientific observation, or assertions, as well as the work of other scientists. If the answer is already known, a different question that builds on the evidence can be posed. When applying the scientific method to research, determining a good question can be very difficult, and it will affect the outcome of the investigation. Hypothesis. Hypothesis is a conjecture based on knowledge obtained while formulating the questions that may explain any given behavior. The hypothesis might be very specific or it might be broad. A statistical hypothesis is a conjecture about a given statistical population. A null hypothesis would conjecture that the statistical hypothesis is false. And that'll be a topic also for future discussions is the philosophy of statistics and the statistical nature, and the multiple truth hypothesis lies within statistics to some extent. Prediction. The prediction step deduces the logical consequence of the hypothesis before the outcome is known. These predictions are expectations for the result of testing. If the result is already known, it is evidence that it is ready to be considered in acceptance or rejection of the hypothesis. The evidence is also stronger if the actual result of the predictive test is not already known, as tampering with the test can be ruled out, as can hindsight bias. Ideally, the prediction must also distinguish the hypothesis from likely alternatives. If two hypotheses make the same prediction, observing the prediction to be correct is not evidence for either one over the other. These statements about the relative strength of evidence can be mathematically derived using Bayes' theorem. The consequence, therefore, is to be stated at the same time or briefly after the statement of the hypothesis, but before the experimental result is known. Likewise, the test protocol is to be stated before execution of the test. These requirements become precautions against tampering and aid the reproducibility of the experiment. Testing. Suitable tests of a hypothesis compare the expected values from the test of the hypothesis with the actual results of those tests. Scientists can then secure or discard their hypothesis by conducting suitable experiments. Analysis. An analysis determines from the results of the experiments the next actions to take. The expected values from the test of the expected values from the test of the alternative hypothesis are compared to the expected values resulting from the null hypothesis, that is, prediction of no difference in the status quo. The difference between the expected versus actual indicates which hypothesis better explains the resulting data from the experiment. In cases where an experiment is repeated many times, a statistical analysis, such as a chi-squared test, whether the null hypothesis is true, may be required. Evidence from other scientists and from experience are available for incorporation at any stage in the process, depending on the complexity of the experiment. Iteration of the process may be required to gather sufficient evidence to answer the question with confidence or to build up other answers to highly specific questions to answer a single broader question. When the evidence has falsified the alternative hypothesis, a new hypothesis is required. If the evidence does not conclusively justify discarding the alternative hypothesis, other predictions from the alternative hypothesis might be considered. Pragmatic considerations such as the resources available to continue inquiry might guide the investigator's further course. When evidence for the hypothesis strongly supports that hypothesis, further questioning can follow for insight into the broader inquiry under investigation. Other components. The scientific method also includes other components required even when all the iteration of the steps above have been completed. Replication. If an experiment can be repeated to produce the same results, this implies that the original results might have been in error. As a result, it is common for a single experiment to be performed multiple times, especially when there are uncontrollable variables or other indications of experimental error. For significant or surprising results, other scientists may attempt to replicate the results for themselves, especially if those results would be important to their own work. Typically, an experimental group gets the treatment, such as a drug, and the control group gets a placebo. For various types of testing. External review. The process of peer review involves evaluation of the experiment by experts who typically give their opinions anonymously. Some journals request that the experimental provide lists of possible peer reviewers, especially in the field of highly specialized. Peer review does not certify the correctness of the results, only that, in the opinion of the reviewer, the experiments themselves were sound based on the description supplied by the experimenter. If the work passes peer review, which occasionally may require new experiments requested by the reviewers, it will be published in a peer-reviewed scientific journal. The scientific journal that publishes the results indicates the perceived quality of the work. Data recording and sharing. Scientists typically are careful in recording their data, a requirement promoted by Ludwig Fleck and others. Though not typically required, they might be required to supply this data to other scientists who wish to replicate their original results or part of their original results, extending the sharing of experimental samples that may be difficult to obtain. Instrumentation. Institutional researchers might acquire an instrument to institutionalize their test. These instruments use observations of the real world, which might agree with or perhaps conflict with their predictions deduced from their hypothesis. These institutions thereby reduce the research function to cost benefit, which is expressed as money and the time and attention of the researchers to be expended in exchange for a report to their constituents. Current large instruments, such as CERN's Large Hadron Collider, the National Ignition Facility, or the International Space Station, or the James Webb Space Telescope, entails expected costs of billions of dollars and timeframes extending over decades. These kinds of institutions affect public policy on a national or even international basis, and the researchers would require shared access to such machines and their adjunct infrastructure. Elements of the scientific method. There are different ways of outlining the basic method used for scientific inquiry. The scientific community and philosophers of science generally agree on the scientific classification of method components. These methodological elements are organized of procedures tend to be more characterized of experimental scientists than social scientists. Nonetheless, the cycle of formulating hypotheses, testing, and analyzing the results, and formulating new hypotheses will resemble the cycle described below. The scientific method is an iterative, cyclical process through which information is continually revised, is generally recognized to develop advances in knowledge through the following elements in varying combination or contributions: characterizations, observations, definitions, and measurements of the subject to inquiry, hypothesis, theoretical, hypothetical explanations of observation and measurements of the subject, predictions, inductive and deductive reasoning from the hypothesis or theory, experiment, tests of all of the above. Each element of the scientific method is subject to peer review for possible mistake. These activities do not describe all that scientists do, but apply mostly to experimental sciences. The scientific method is not a single recipe. It requires intelligence, imagination, and creativity. In this sense, it is not a mindless set of standards and procedures to follow, but is rather an ongoing cycle, constantly developing more useful, accurate, and comprehensive models and methods. An iterative, pragmatic scheme of the 4 points above is sometimes offered as a guideline for proceeding. Define a question. 2, gather information and resources. Observe. 3, form an explanatory hypothesis. 4, test the hypothesis by performing an experiment and collecting data in a reproducible manner. 5, analyze the data. 6, interpret the data and draw conclusions that serve as a starting point for a new hypothesis. 7, publish the result. 8, retest, frequently done by other scientists. The iterative cycle inherent in this step-by-step method goes from point 3 to 6 back to 3 again. Form an explanatory hypothesis, test the hypothesis by performing an experiment and collecting data in a reproducible manner, analyze the data, interpret the data, and draw conclusions that serve as a starting point for a new hypothesis. While the schema outlines a typical hypothesis testing method, many philosophers, historians, and sociologists of science, including Paul Feyerabend, claim that such descriptions of a scientific method have little relation to the way that science is actually practiced. The scientific method depends upon increasingly sophisticated characterizations of the subjects of investigation. The subjects can also be called unsolved problems or the unknowns. For example, Benjamin Franklin conjectured correctly St. Elmo's fire was electrical, but it took a long series of experiments and theoretical changes to publish this. While seeking the pertinent properties of subjects, careful thought may also entail some definitions and observation. The observations often demand careful measurements and or counting. The systemic careful collection of measurement or counts of relevant quantities is often the critical difference between pseudoscience such as alchemy and science such as chemistry or biology. Scientific measurements are usually tabulated, graphed, or mapped, and statistical manipulations such as correlation and regression performed on them. The measurements might be made in a controlled setting, such as a laboratory, or made on more or less inaccessible or unmanipulable objects such as stars or human populations. The measurements often require specialized scientific instruments such as thermometers, spectroscopes, particle accelerators, or voltmeters, and the progress of a scientific field is usually intimately tied to their invention and improvement. And measurement is a field I'm going to go much more in depth into in the near future. Uncertainty. Measurement in scientific work are also usually accompanied by estimates of their uncertainty. The uncertainty often estimated by making repeated measurements of the desired quantity. Definition. Measurements demand the use of operational definitions of relevant quantities. That is, scientific quantity is described or defined by how it is measured, as opposed to some more vague, inexact, or idealized definition. For example, electric current measured in amperes may be operationally defined in terms of the mass of silver deposited in a certain time on an electrode in an electrochemical device that is described in some detail. The operational definition of a thing often relies on comparisons with standards. The operation definition of mass ultimately relies on the use of an artifact, such as a particular kilogram of platinum iridium kept in a laboratory in France. The scientific definition of terms sometimes differs substantially from its natural language usage. For example, mass and weight overlap in common meaning and common discourse, but have distinct meanings in mechanics. Scientific quantities are often characterized by their units of measure, which can later be described in terms of conventional physical units when communicating their work. New theories are sometimes developed after realizing certain terms have not previously been sufficiently clearly defined. The measurement problem is a topic that I will be covering in depth and is extremely important for the further development into modern science, and the heart between some of the divisions of metaphysics, philosophy, and science, because science is simply the method applied to what is measurable, as where the metaphysics might take a different turn. Hypothesis development. Hypothesis is a suggested explanation of a phenomenon, or alternatively, a reasoned proposal suggesting a possible correlation between or among a set of phenomena. Normally, hypotheses have the form of a mathematical model. Sometimes, but not always, they can also be formulated as an existential statement, stating that some particular instance of the phenomenon being studied has some characteristics and causal explanation, which have the general form of universal statements, stating that every instance of the phenomenon has a particular characteristic. Scientists are free to use whatever resources they have, their own creativity, ideas from other fields, inductive reasoning, Bayesian inference, and so on, to imagine possible explanations for a phenomenon under study. Albert Einstein once observed that there is no logical bridge between phenomenon and their theoretical principles. Charles Sanders Peirce, borrowing a page from Aristotle, described the incipient stages of inquiry instigated by the irritation of doubt to venture a plausible guess as abductive reasoning. The history of science is filled with stories of scientists claiming a flash of inspiration or a hunch, which then motivated them to look for evidence to support or refute their idea. Michael Polanyi made such creativity the centerpiece of his discussion on methodology. William Glenn observed that the success of a hypothesis or its service to science lies not simply in its perceived truth or power to displace, subsume, or reduce a predecessor idea, perhaps more in its ability to stimulate the research that will illuminate bold suppositions and areas of vagueness. In general, scientists tend to look for theories that are elegant or beautiful. Scientists often use these terms to refer to a theory that is following the known facts, but is nevertheless relatively simple and easy to handle. Occam's razor serves as a rule of thumb for choosing the most desirable among a group of equally explanatory hypotheses. To minimize the confirmation bias which results from entertaining a single hypothesis, strong inference emphasizes the need for entertaining multiple alternative hypotheses. Predictions and hypotheses. Any useful hypothesis will enable predictions by reasoning, including deductive reasoning. It might predict the outcome of an experiment in a laboratory setting or the observation of a phenomenon in nature. The prediction can only be statistical and deal only with probabilities. It is essential that the outcome of testing such as a prediction be currently unknown. Only in this case does a successful outcome increase the probability that the hypothesis is true. If the outcome is already known, it is called a consequence and should have already been considered while formulating the hypothesis. If the predictions are not accessible by observation or experience, the hypothesis is not yet testable and will remain, to the extent, unscientific in a strict sense. A new technology or theory might make the necessary experiments feasible. For example, while a hypothesis of the existence of other intelligent species may be convincing with scientifically based speculation, no known experiment can test this hypothesis. Therefore, science itself can have little to say about the possibility in the future. A new technique may allow for an experimental test, and the speculation would then become part of the accepted science. Experiments. Once predictions are made, there can be sought by experiments. They can be sought by experiments. If the test results contradict the predictions, the hypothesis which entailed them are called into question and become less tenable. Sometimes the experiments are conducted incorrectly, or they're not very well designed when compared to a crucial experiment. If the experiment results confirm the predictions, then the hypotheses are considered more likely to be correct, but might still be wrong and continue to be subject to further testing. The experimental control is a technique for dealing with observational error. The technique uses a contrast between multiple samples or observation or populations under differing conditions to see what varies and what remains the same. We vary the conditions for the acts of measurement to help isolate what has changed. Mills can then help us figure out what the important factor is. John Stuart Mill factors and analysis is one technique for discovering the important factor in an effect. Depending on the predictions, the experiments can have different shapes. It could be a classical experiment in a laboratory setting, a double-blind study, or an archaeological excavation. Scientists assume an attitude of openness and accountability on the part of those experimenting. Detailed record keeping is essential to aid in recording and reporting the experimental results and supports the effectiveness and integrity of the procedure. They will also assist in reproducing the experimental results likely by others. Traces of this approach can be seen in the work of Hippocrates when determining the value of the precession of the earth, while controlled experiments can be seen in the works of Al-Battani and Alhazen. Evaluation and improvement. The scientific method is iterative. At any stage, it is possible to refine its accuracy and precision so that some considerations will lead the scientist to repeat an earlier part of the process. Failure to develop an interesting hypothesis may lead to a scientist to redefine the subject under consideration. Failure of hypothesis to produce interesting and testable predictions may lead to reconsideration of the hypothesis or of the definition of the subject. Failure of an experiment to produce interesting results may lead a scientist to reconsider the experimental method, the hypothesis, or the definition of the subject. Other scientists may start their own research and enter the process at any stage. They might adapt the characterization and formulate their own hypothesis, or they might adopt the hypothesis and produce their own predictions. Often the experiment is not done by the person who made the prediction, and the characterization is based on experiments done by someone else. Published results of experiments can also serve as hypotheses predicting their own reproducibility. Confirmation. Science is a social enterprise, and scientific work tends to be accepted by the scientific community when it has been confirmed. Crucially, experiments and theoretical results must be reproduced by others within the scientific community. To protect against bad science and fraudulent data, government research granting agencies such as the National Science Foundation and science journals, including Nature and Science, have a policy that researchers must archive their data and methods so that other researchers can test the data and methods and build on the research that has gone before. Scientific data archiving can be done at several national archives in the U.S. The World Data Center. Scientific inquiry. Scientific inquiry generally aims at obtaining knowledge in the form of testable explanations the scientists can use to predict the results of future experiments. This allows scientists to gain a better understanding of the topic under study and later to use the understanding to intervene in its causal mechanisms. The better the explanation is at making predictions, the more useful it frequently can be, and the more likely it will continue to explain a body of evidence better than its alternatives. The most successful explanations, those which explain and make accurate predictions in a wide range of circumstances, are often called scientific theories. Most experimental results do not produce large changes in human understanding. Improvements in theoretical scientific understandings typically result from gradual process of development over time, sometimes across different domains of science. Scientific models vary in the extent to which they have been experimentally tested and for how long, and in their acceptance in the scientific community. In general, explanations become accepted over time as evidence accumulates on a given topic, and the explanation in question proves more powerful than its alternative at explaining the evidence. Often subsequent researchers reformulate the explanations over time or combined explanations to produce new explanations. Properties of scientific inquiry. Scientific knowledge is closely tied to empirical findings and can remain subject to falsification if new experimental observations are incompatible with what is found. That is, no theory can ever be considered final since the new problematic evidence might be discovered. If such evidence is found, new theory may be proposed, or more commonly it is found that modifications to the previous theory are sufficient to explain the new evidence. The strength of the theory relates how long it has persisted without major alteration to its core principles. Theories can also become subsumed by other theories. For example, Newton's laws explained thousands of years of scientific observations. Since new theories might be more comprehensive than what preceded them and thus be able to explain more than previous ones, successor theories might be able to meet a higher standard by explaining a larger body of observation than their predecessors. So unfortunately, I had an error at this point with the unfortunately, I had an error at this point with the highlighting app, so I wasn't able to highlight it properly. So I'm going to read a little bit more from this, but unfortunately, it got all highlighted in yellow. But I'm almost done with this section. Some of this is actually pretty important, so I didn't want to skip this, even though I had an error with the highlighter program. Beliefs and biases. Scientific methodology often directs the hypothesis to be tested in controlled conditions wherever possible. This is frequently possible in certain areas, such as biological sciences, and more difficult in other areas, such as astronomy. The practice of experimental control and reproducibility can have the effect of diminishing the potential harmful effects of circumstances and, to a degree, personal bias. So Fleck, we mentioned a few times now, words and ideas are originally phonetic and mental equivalences of the experience coinciding with them. Such proto-ideas are at first always too broad and insufficiently specialized. Once structurally complete and closed systems of opinions consisting of many details and relations have been formed, it offers enduring resistance to anything that contradicts it. Sometimes these relations have their elements assumed a priori or contain some other logical or methodological flaw in the process that has ultimately produced them. Models of scientific inquiry. So the classical model of scientific inquiry derives from Aristotle, who distinguished the forms of approximate and exact reasoning, set out the threefold scheme of abductive, deductive, and inductive inference, and also treated the compound forms such as reasoning by analogy. The hypothetical deductive model, and we'll be covering this in depth, it's very important. The hypothetical deductive model or method is proposed description of the scientific method. Here, predictions from the hypothesis are central. If you assume the hypothesis to be true, what consequences follow? If a subsequent empirical investigation does not demonstrate these consequences or prediction corresponding to the observable world, the hypothesis can be concluded to be false. The pragmatic model, and this relates to Charles Sandre Peirce, who we've discussed multiple times, and he actually calls it the pragmatic theory of truth in relation to the multiple truth hypothesis in terms of the questionable relationship between science and truth. I'm going to read through this, even though it's a little bit at length because it's somewhat directly related to the multiple truth hypothesis. 1877, Charles Sanders Peirce characterized inquiry in general not as the pursuit of truth per se, but as the struggle to move from irritating, inhibitory doubts born of surprises, disagreements, and the like, and reach a secure belief, the belief being that on which one is prepared to act. He frames scientific inquiry as part of the broader spectrum and is spurred, like inquiry generally, by actual doubt, not merely verbal or hyperbolic doubt, which he held to be fruitless. He outlined four methods of settling opinions, ordered from least to most successful. 1. The method of tenacity, policy of sticking to initial belief, which brings comfort and decisiveness but leads to trying to ignore contrary information and others' views as if truth were intrinsically private, not public. It goes against the social impulse and easily falters, since one may well notice when another opinion is good as one's own initial opinion. Its successes can shine but tend to be transitory. 2. The method of authority, which overcomes disagreements but sometimes brutally. Its successes can be majestic and long-lived, but it cannot operate thoroughly enough to suppress doubts indefinitely, especially when people learn of other societies past and present. 3. The method of a priori, which promotes conformity less brutally but fosters opinions as something like taste, arising in conversation and comparisons of perspective in terms of what is agreeable to reason, thereby depends on fashion and paradigms and goes in circles over time, is more intellectual and respectable, but like the first two methods, sustains accidental and capricious beliefs, destining some minds to doubt it. 4. The scientific method, the method where an inquiry regards itself as fallible and purposely tests itself and criticizes, corrects, and improves itself. Peirce held that slow, stumbling ratiocination can be dangerously inferior to instinct and traditional sentiment in practical matters, and that the scientific method is best suited to theoretical research, which in turn should not be trammeled by the other methods and practical ends. Reason's first rule is that in order to learn, one must desire to learn, and as a corollary, must not block the way of inquiry. The scientific method excels the others by being deliberately designed to arrive eventually at the most secure beliefs upon which the most successful practices can be based, starting from the idea that people seek not truth per se, but instead the subdue irritating inhibitory doubt. Peirce showed how Through the struggle, some could come to submit to the truth for the sake of belief's integrity, seek as truth the guidance of potential practice correctly for its goal, and wed themselves to the scientific method. For Peirce, rational inquiry implies presuppositions about truth, and the real to reason is to presuppose as a principle of the reasoner's self-regulation that the real is discoverable and independent of our vagaries of opinions. In that vein, he defined truth as the correspondence of a sign to its object, and pragmatically not as the actual consequence of some definite finite community, but instead as the final opinion which all investigations would reach sooner or later, but still inevitably if they were to push investigation far enough, even when they start from different points. In tandem, he defined the real as a true science object, which is what it is, independent of any finite community's opinion, and pragmatically dependent only upon the final opinion destined in sufficient investigation. This is a destination as far or near as the truth itself to you or me or the given finite community. Thus, his theory of inquiry boils down to do the science. The conceptions of truth are the real, and the real involve the idea of community both without definite limits and capable of definite increase of knowledge. As in inference, logic is rooted in the social principle, since it depends on a standpoint that is in sense unlimited. Paying special attention to the generation of explanation, Peirce outlined the scientific method as coordination of three kinds of inference in a proposed cycle aimed at settling doubts of abduction, deduction, and induction, is similar to Aristotle. Abduction, guessing inference to explanatory hypothesis for selection of those best worth trying. From abduction, Peirce distinguishes induction as inferring based on test the proportion of truth in the hypothesis. Every inquiry, whether into ideas, brute facts, or norms and laws, arises from surprising observation in one or more of those realms. All explanatory content of theories comes from abduction, which guesses a new or outside idea to account in a simple economical way for a surprising or complicative phenomenon. Oftenest, even a well-prepared mind guesses wrong, but the modicum of success of our guesses far exceeds that of sheer luck and seems born of attunement by nature to nature by instincts developed of inherent, especially insofar as best guesses are optimally plausible and simple in their sense, said Peirce, of the facile and natural, as by Galileo's natural light of reason, and by distinct from logical simplicity. Abduction is the most fertile but least secure mode of inference. Its general rationale is inductive. It succeeds often enough, and without it, there is no hope of sufficiently expediting inquiry towards new truth. Coordinative methods lead to abducing a plausible hypothesis, to judging its testability, and for how its trial would economize inquiry itself. Peirce calls his pragmatism the logic of abduction. His pragmatic maxim is consider what effects that might conceivably have practical bearings you conceive the objects of your conception to have. Then your conception of those effects is the whole of your conception of the object. His pragmatism is a method of reducing conceptual confusions fruitfully by equating the meaning of any conception with the conceivable practical implication of the object's conceived effects, a method of experimentational mental reflection hospitable to forming hypotheses and conducive to testing them. It favors efficiency. The hypothesis being insecure needs to have practical implications leading at least to a mental test, and in science, lending themselves to scientific test. A simple but unlikely guess, if uncostly to test for falsity, may belong first in line for testing. A guess is intrinsically worth testing if it has instinctively plausible or reasonable objective probability, while subjective likelihood, though reason, can be misleadingly seductive. Guesses can be chosen for trial strategically for their caution, breadth, and in complexity. One can hope to discover only that which time would reveal through a learner's sufficient experience anyway, so the point is to expedite the economy of research is what demands the leap, so to speak, of abduction and governs its art. Deduction, 2 stages. Explication, unclearly premised but deductive analysis of the hypothesis in order to render its parts as clear as possible. demonstration, deductive argumentation, Euclidean in procedure, explicit deduction of hypothesis, consequences as prediction for induction to test about evidence to be found, collateral, or if indeed theoretic. Induction, the long-run validity of the rule of induction is deducible from the principle that the real is the only object of the final opinion to which adequate investigation would lead. Anything to which no process would ever lead would not be real. Induction involves ongoing test or observation, follows a method which, sufficiently persisted in, will diminish its error below any predesignate degree. 3 stages. 1, classification, unclearly premised but inductive, classing of objects of experience under general ideas. 2, probation, direct inductive argumentation, crude, the enumeration of instances or gradual new estimates of the proportion of truth in the hypothesis after each test. Gradual induction is qualitative and quantitative. If qualitative, then dependent on weightings of qualities or characters. If quantitative, then dependent on measurements or on statistics or on countings. Sentental induction. 3, sentental induction, which is by inductive reasoning appraises the different probations singly, then their combinations, then makes self-appraisal of these various appraisals themselves and passes final judgment on the whole result. So I'm glad I'm reading through this. So I hope some people find this interesting. It's almost for my own purposes here. And as I move forward in the multiple truth hypothesis, I want to firmly be grounded in the knowledge that's currently out there. So the next, the invariant explanation, Ralph from the House of Comments, one of his favorite philosophers of science, David Eliezer Deutsch from Israel, Oxford in Israel. 2009 TED Talk, Deutsch expounded a criterion for scientific explanation, which is to formulate invariants. State an explanation publicly so that it can be dated and verified by others later that remains invariant in the face of apparent change, new information, or unexpected condition. A bad explanation is easy to vary. The search for hard-to-vary explanation is the origins of all progress. That the truth consists of hard-to-vary assertions about reality is the most important fact about the physical world. Invariance is a fundamental aspect of scientific account of reality has long been part of philosophy of science. And finally, community and communication and the importance of peer review. Frequently, the scientific method is employed not only by a single person, but also by several people cooperating directly or indirectly. Such cooperation can be regarded as an important element of a scientific community. Various standards of scientific methodology are used within such an environment. Peer review evaluation. Scientific journals use a process of peer review in which scientists' manuscripts are submitted by editors of scientific journals, fellow scientists familiar with the field, for evaluation. In certain journals, the journal itself selects the referees, while in others, the manuscript author might recommend the referees. The referees may or may not recommend publication, or they might recommend publication with suggested modifications or sometimes publication in another journal. The standard is practiced to varying degrees by different journals and can have the effect of keeping the literature free of obvious errors and generally improve the quality of the material, especially in the journal that use the standard most rigorously. The peer review process can have limitations when considering research outside the conventional scientific paradigm. Problems of groupthink can interfere with open and fair deliberation of some new research. Documentation and replication. Sometimes experimenters may make systematic errors during their experiments, veer from standard methods and practices for various reasons, or in rare cases, deliberately report false results. Occasionally, because of this, other scientists might attempt to repeat the experiments to duplicate the results. Archiving. Researchers sometimes practice scientific data archiving, such as in compliance with the policies of government funding agencies and scientific journals. In these cases, detailed recording of the experimental procedures, raw data, statistical analysis, and source code can be preserved to provide evidence of the methodology and practice of the procedure and assist in any potential future attempts to reproduce the results. These procedures records may also assist in the conception of new experiments and to test hypotheses, and may prove useful to engineers who might examine the potential and practical implications of a discovery. Data sharing. When additional information is needed before a study can be reproduced, the author of the study might be asked to provide it. they might provide it, or if the author refuses to share the data, appeals can be made to the journal editors who published the study or to the institution which funded the research. Limitations. Since a scientist can't record everything that took place in experiments, facts selected from the apparent relevance are reported. This may lead unavoidably to problems later if some supposedly irrelevant feature is questioned. The problem is that parts of the theory itself need to be assumed to select and report experimental condition. The observation are hence sometimes described as being theory-laden. And there's a lot more here, but I think I'm going to cover this part about mathematics also. Relationship with mathematics. Science is the process of gathering, comparing, and valuing proposed models against observables. A model can be a simulation, mathematical or chemical formula, or a set of proposed steps. Science is like mathematics in that researchers in both disciplines try to distinguish what is known from what is unknown at each stage of discovery. Models in both science and mathematics need to be internally consistent and also ought to be falsifiable. In mathematics, statements need not yet be proved. At such stage, that statement would be called a conjecture. But when a statement has attained mathematical proof, the statement gains a kind of immortality which is highly prized by mathematicians and for which some mathematicians devote their life. Mathematical works and scientific work can inspire others. For example, the technical component of time arose in science, and timeliness was a hallmark of a mathematic topic. But today, the Poincare conjecture has been proved using time as a mathematical concept in which objects can flow. Nevertheless, the connection between mathematics and reality, and so science to the extent it describes reality, remains obscure. Eugene Wigner's paper, The Unrealizable Effectiveness of Mathematics in Natural Science, is well-known account of the issues from a Nobel Prize-winning physicist. In fact, some observers have suggested that mathematics is the result of practitioner bias and human limitation, somewhat like the postmodernist view of science. George Polya's work on problem solving, the construction of mathematical proofs and heuristics, shows that the mathematical method and the scientific method differ in detail while nevertheless resembling each other in using iterative or recursive steps. So the mathematical method, understanding, analysis, synthesis, review, extend. The scientific method, characterization from experience and observation, hypothesis, proposed explanation, deduction, prediction from the hypothesis, test, and experiment. In Polya's view, understanding involves restating unfamiliar definitions in your own words, resorting to geometric figures, and questioning what we know and what we do not know already. Analysis, which Polya takes from Pappas, involves free and heuristic construction of plausible arguments, working backwards from the goal and devising a plan for constructing the proof. Synthesis, and the strict Euclidean exposition of step-by-step details of the proof. And review involves reconsidering and re-examining the results and the path taken to it. Building on Polya's work, Imre Lakatos argued that mathematicians actually use contradiction, criticism, and revision as principles for improving their work in a manner to science whose truth is sought but certainly not found. In Proofs and Refutations, what Lakatos tried to establish was that no theorem of informal mathematics is final or perfect. This means that we should not think that a theorem is ultimately true, only that no counterexample has yet been found. Once a counterexample, an entity contradicting not explained by the theorem is found, we adjust the theorem, possibly extending the domain of its validity. This is a continuous way our knowledge accumulates through the logic and processes of proof and refutation. Lakatos proposed an account of mathematical knowledge based on Polya's ideas of heuristics and proofs and refutation. Lakatos gave several basic rules for finding proofs and counterexamples to conjectures. He thought that mathematics thought experiments are a valid way to discover mathematical conjectures and proof. Gauss, when asked how he came to his theorems, once replied, through systematic, palpable experimentation. Relationship with statistics. When the scientific method employs statistics as a key part of its arsenal, there are mathematical and practical issues that can have a deleterious effect on the reliability of the output of a scientific method. This is described in the popular 2005 scientific paper, Why Most Published Researchers' Findings Are False by John Ioannidis, which is considered foundational to the field of metascience. Much research in metascience seeks to identify poor use of statistics and improve its use. The particular points raised are statistical. The smaller the studies conducted in the scientific field, the less likely the research findings are to be true, and the greater the flexibility in designs, definitions, outcome, and analytical modes in the scientific field, the less likely the research findings are to be true. And economically, the greater the financial and other interest and prejudices in the scientific field, the less likely the research finds are to be true. And the hotter a scientific field with more scientific teams involved, the less likely the research findings are to be true. Hence, most research findings are false for most research designs and for most fields. And as shown, the majority of modern biomedical research is operating in areas with very low pre and post study probability for true findings. However, nevertheless, most new discoveries will continue to stem from hypothesis generating research with low or very low pre study odds, which means that new discoveries will come from the research that, when the research started, had low or very low odds of succeeding. Hence, the scientific method is used to expand the frontiers of knowledge. Research into areas that are outside of the mainstream will yield the newest discoveries. In the role of chance in discovery, somewhere between a third and a half of all scientific discoveries are estimated to have been stumbled upon rather than sought out. This may explain why scientists so often express that they were lucky. Psychologist Kevin Dunbar says the process of discovery often starts with research, finding bugs in their experiments. These unsuspected results lead researchers to try to fix what they think is an error in their method. Eventually, the researcher decides the error is too persistent and systematic to be a coincidence. The highly controlled, cautious, and curious aspects of the scientific method are thus what make it well suited for identifying such persistent, systematic errors. At this point, the researchers will begin to think of theoretical explanations for the error, often seeking the help of colleagues across different domains of expertise. Okay, so I see my audience dwindle away. So hopefully some people will benefit from this later. And a lot of this is purely for my own benefit and to advance my theory. So, I'm just publicly putting my studies out there, and I want to ground into my head a proper understanding of this. So, it'd be kind of boring. I can understand that no one really wants to watch me just read a Wikipedia on some of this stuff. But, say Duvid is avowing myself to the scientific process and trying to push forward my ideas, and therefore I want to fully be grounded in science and in the ideas and do the due diligence and just accuracy. I want to be accurate. I want to actually, know what I'm talking about and quote my sources. If I'm saying something unique and new, to know that I'm saying something unique and new, and that I have to do the due diligence of the research. And personally, I just find this stuff interesting, honestly. So, like, I've read hundreds of books, really. Like, over the last few months, I've been reading, like, almost 2 books a day on the subject. And so, just to make sure it's not just flowing in and out, I'm putting some information out there, and I don't know exactly how to do it. So, for now, I'm just reading straight through. And so hopefully some people will find this a little bit useful. Let's take a break for a second. Okay. So this is probably extremely important. Like, for relatively what I'm doing today, this is probably like the most important that I'm going to do. And moving forward, I appreciate the positive feedback, Conway. Moving forward, Kant is going to become like the cornerstone to the modernist. And I'm going to get into neo-Kantianism and the Vienna School and modern mechanics, and also philosophy of mind, identity theory. Kant is usually where people get lost and like, okay, like I'm a Jew and have Judeo philosophy, and Kant was a contemporary opponent of Moses Mendelssohn. Kant had run-ins with Moses Mendelssohn. Kant was a critic of Judaism, and like Adam Green of his day to a certain extent. However, Kant's basis of theories of knowledge, philosophy of science, are probably the most important today for modern science. So I want to cover quite a bit of this, and I'm going to skip the part about his metaphysics of mechanics and motion and the nature of space. I may return in the future to some of these concepts. I've talked about it in the past. This should be a little bit more interesting. The viewership, part of the scientific method, was just kind of due diligent for myself to really grind it in to get these principles. I thought the part on Peirce and David Deutsch was also quite interesting, and I might return more to some of the Peirce. But Kant is really important to understand, and like even as like a Jew and looking like Kant's view that you got to really struggle with Kant. And hey, I see three black. Good to see you. You got to really struggle to understand Kant, but as you understand Kant, you could see him as possibly the most important philosopher of the 19th century, especially in the precursors of theory of knowledge, metaphysics, philosophy of science, philosophy of mind, psychology, a whole bunch of topics. So let's jump right in. Kant's philosophy of science has received attention from several different audiences and for a variety of reasons. It is of interest to contemporary philosophers of science, primarily because of the way in which Kant attempts to articulate a philosophical framework that places substantive conditions on our scientific knowledge of the world while still respecting the autonomy and diverse claims of particular sciences. More specifically, Kant develops a philosophy of science that departs from broadly empiricist views, according to which purely contingent events in space and time determine what the laws of nature ultimately are, and certain necessitarian views, according to which the laws of nature consist of necessitation relations between universals, which place constraints on what events occur in space and time. Kant does so by holding that scientific laws do involve necessity, but that this necessity is based not on purely metaphysical and hence inaccessible relations between universals, but rather contains subjective a priori conditions under which we can experience objects in space and time. Kant's scientific writings also are of interest to historians of modern philosophy, historians of science, and historians of philosophy of science. Historians of modern philosophy are especially interested in determining how Kant's views on science might complement or clarify his distinctive metaphysical and epistemological doctrines as expressed in the Critique of Pure Reason. Historians of science reflect on the way in which Kant's positions fits in with the views of other natural philosophers of his period, such as Newton and Leibniz, including his novel account of the formation of the solar system according to Newtonian principles. Historians of philosophy of science investigate, among other things, Kant's work in the conceptual foundation of physics, in particular his matter theory, the infinite divisibility of matter, attractive and repulsive forces, inertia, atoms, and the void. His theory of motion is a dynamical account of the laws of mechanics. Because physics was Kant's primary, though not exclusive, focus over the course of his lengthy career, his views on physics during his critical period, crucial and post-critical crucial periods will be discussed in separate sections. Subsections will be devoted to each of these chapters of Kant's most influential work in the philosophy of science, the metaphysical foundations of natural science. 1786, Kant's basic position on other sciences, including psychology, chemistry, and history, will be presented thereafter. And so I'm actually going to read large sections from all of this. And I say, like, of the utility of what I'm reading, many of the other stuff was due diligent. The stuff on the models and Locke are important, but Kant is, some of these points of Kant are going to come back, and especially when I get into the neo-Kantianism that discussed somewhat on Week in Review that leads into the modern period. So say the neo-Kantians don't accept everything that Kant says is true and largely reject it, but so to say that Kant kind of developed a comprehensive system for understanding science, was part of the process of the synthesis of Leibniz, Descartes, and Newton, and forms the basis for the philosophy of science moving forward. So the Neo-Kantians don't take like Kant as gospel, but form Kant's metaphysics as the basis to push the philosophy of science. So even a lot of the Jewish uh, philosophers of science like Popper and Kuhn, and even the Marburg School, the Neo-Kantians, a lot of them are Jewish. However, they rely upon the Kantian metaphysics. So over the next few weeks, this will be extremely important. And I think I put the link in the chat. So if anyone is studious and wants to read along, encourage them to. And physics, the pre-critical period. Kant's early pre-critical publications, 1746 to 56, are devoted primarily to solving a variety of broadly cosmological problems and developing an increasingly comprehensive metaphysics that would account for the matter theory that is required by the solution to these problems. Kant's first publications, Thoughts on the True Estimation of Living Forces, 1746, explicitly attempts to solve the vis vis controversy, which had been hotly contested ever since Leibniz's attack on Descartes' laws of motion in the Acta Juridicum 1686, while Kant's attempts to occupy an intermediate position between the Cartesian and Leibnizian positions by maintaining that both mv and mv squared, which is momentum and acceleration. Momentum and so I mean these formulations, when you look into the early formulation of physics, are become. We'll talk about it more. I'm going to skip a little part of the actual physics part of it. We're looking for the metaphysical foundations of the early formulations of physics laws, and eventually the Neo-Kantians settle on the conservation of energy. However, as discussed on Week in Review, Leibniz, Newton, the earlier physicists disagreed on what is actually conserved, if it's impulse or momentum. What is of particular note is how the solution rests upon the conception of force developed in Part 1. According to this conception, force is understood in terms of the activity of substance as activity that Kant then used his explanation of how the motions of bodies are generated to solve the mind-body problem and to account for both the possibility of other actually existing worlds in the three-dimensionality of space. His solution to the vis-a-vis dispute is especially interesting because it presage his later approach to philosophical controversy. Rather than offering a conclusive argument in favor of one position, Kant seeks to mediate between the two parties, Leibnizian and Cartesian. He argues that each measure of force is correct, but in different contexts. Kant distinguishes the two ways of studying bodies, mathematical and metaphysical, and claims that they presuppose distinct conceptions of body according to mathematical mechanics. A body cannot accelerate unless an external cause acts upon it. For that reason, Kant declares the Cartesian quantity mv, mass times velocity, is the only one appropriate for measure of force in this context. Natural bodies, in contrast, have features that mathematics brackets. One such feature is the capacity of vivification, whereby a body increases by itself the force of motion that an external cause merely awakens. In light of that, Kant concludes the Leibnizian quantity, mass times velocity squared, is the correct measure of force and metaphysical considerations of natural bodies. So this becomes confusing because today mass times velocity squared is momentum, and force is acceleration, is mass times acceleration. And so looking at the pre-canonical formulation could become a little bit confusing, and then trying to connect the metaphysics between what does it mean velocity squared. And if you look like, okay, mathematically or graphically, geometrically, possibly you can understand, but metaphysically, does it even mean anything? Doesn't even make sense. And that goes back to the question of modeling mathematics to the target system of real world bodies. And that's why Kant is seen as so difficult, but at the same time is so important. Kant develops his account of the nature of substance in great detail in a new elucidation of the first principles of metaphysical cognition, 1755. While the first two sections of this work undertake revisions of Wolff's principle of non-contradiction and sufficient reason, the third section argues for two substantial principles that are alleged to follow from the principle of sufficient reason, namely the principle of succession and coexistence. The main thrust of the principle of succession is directed against Leibnizian pre-established harmony, arguing that only causal connections between substances can bring about change in their states. Kant's position appears to be designed to account primarily for change of body states, with changes in mental states being parasitic upon them, as was explicitly asserted in True Estimation. For he maintains that mutual changes of state require mutual interaction, where it is clear that changes in motion are precisely the kind of mutual change that he has in mind, since one body cannot move closer to another without the other body moving closer to it. The principle of coexistence then argues that a harmonious causal interaction between otherwise isolated, independently existing substances is possible only by means of God's coordination, just as Leibniz thought was required for harmonious relations between the states of such substances. Kant's physical monadology, 1756, takes the task the reconciliation of the infinite divisibility of space as maintained in geometry with the simplicity of substances, which Kant believes is required in metaphysics. As was his case in his earlier works, the essential feature of his reconciliation lies in the way in which his matter theory is supported by his metaphysical views. Specifically, Kant asserts the simple substance fills space not by means of their mere existence, but rather in virtue of the spheres of activity. As a result, any division of the relevant spheres of activity does not compromise the simplicity of the substances themselves, since the spatial properties of substances, including the infinite divisibility of space, arises from the interaction between their activities rather than from their intrinsic features. In the course of physical monadology, Kant also argues for the necessity of attractive and repulsive forces and attributes a significant role to the force of inertia. Kant's acceptance of such Newtonian principles represents an important change of position over the true estimation, where Kant rejects the principle of inertia and pursues a dynamic theory much more in line with Leibniz's views. In addition to these works, which bridge the gap, as it were, between physics and metaphysics during this period, Kant is interested in a series of specific issues in cosmology and in empirical physics. Of much greater significance is his Universal Natural History and Theory of the Heavens, 1755, which represent an important contribution to science as such, for in it Kant explains how one can account for the formation of the solar system from an initial state in which matter is dispersed like a cloud solely by means of the interaction of attractive and repulsive forces. In 1796, Laplace, unaware of Kant's argument, would develop a very similar derivation, with the result that the view is now typically referred to as the Kant-Laplace nebular hypothesis. Some of Kant's youthful insight have yielded long-lasting contributions to scientific knowledge. His intuition that tides slow down the Earth's rotation over time is correct, and his new remarks towards the elucidation of the theory of winds, Kant correctly explained that north-south winds in our hemisphere suffer a Coriolis deflection due to Earth's rotation. Moreover, broadly Kantian accounts of planetary formation have been the dominant model since the emergence of the sophistication nebular models in the 1970s. Later in the pre-critical period, 1763 to 1770, Kant attempts to build a comprehensive metaphysical account of the basis of the framework that he established in his first works, thus in his The Only Possible Basis for the Demonstration of the Existence of God, 1763. He attempts to extend his reasoning to fundamental issues in both philosophical theology and theology, presenting for the first time in his famous criticism of the three traditional arguments for the existence of God, while developing a new theistic proof based on the idea that God is necessary as a real ground of the possibilities of things. After reading Hume's inquiry concerning human understanding in German translation sometime after 1755, Kant distinguishes between real and logical grounds, oppositions in his attempt to introduce the concept of negative magnitudes into philosophy, 1763, to avoid Hume's objection that there is no logical contradiction in the existence of one thing not following the existence of another. But in this work, he also is interested in exploring the notion of the real ground opposition further by applying it more widely to bodies, mental states, so on. As relevant is Kant's concerning the ultimate foundation of the distinction of the direction of space, 1768, which modifies his earlier account of space insofar as he seems to hold that empirical spatial properties, uh, chirality or handedness, may not be able to explain entirely in terms of direction relation between material substances. The so-called inaugural dissertation, 1770, Kant continues to develop a more comprehensive philosophical system which would encompass the principles of both the sensible and intelligible world, and in so doing modifies his account of space and time even further. Over the course of the next 10 years, during which he published almost nothing, Kant would revise his views more systematically, with the publication of the Critique of Pure Reason in 1781 representing the first major step in his critical turn. Physics, the critical period, metaphysical foundations of natural science. So this section goes over chapter by chapter, and I'm going to skip a reasonable amount of this because a lot of this is on the metaphysics of matter and space. In the preface to the Metaphysical Foundation, Kant analyzes the concept of nature and science as to establish what conditions must be met for a body of knowledge to constitute natural science in its proper sense, explains why science, so understood, requires a pure part, and what criteria would have to be satisfied for such a pure part to exist, argues that chemistry and psychology cannot at present meet these criteria, and describes what procedures should be followed to satisfy these criteria and thus to provide the pure part that science proper requires. The feature of Kant's conception of natural science proper is that most immediately striking is how restricted it is. It requires that cognition be systematically ordered according to rational principles and to be a priori with apodictic certainty, with consciousness of their necessity. Because properly scientific cognition must satisfy these strict conditions, it requires a pure part on which the apodictic certainty that reason seeks can be based. But since Kant identifies pure rational cognition that is generated from concepts of metaphysics, it follows that science proper requires a metaphysics of nature. He then specifies that such a metaphysics of nature could consist in either a transcendental part, which discusses the laws that make possible the concept of a nature in general, even without relation to any determined object of experience, or a special metaphysical part which concerns a particular nature of this or that kind of things for which an empirical concept is given. Kant's very conception of nature, science proper, thus immediately gives rise to several systematic important questions. First, if the transcendental part of the metaphysics of nature can be identified with the results of the Critique of Pure Reason, then the Metaphysical Foundations is a work in special metaphysics. But what exactly is special metaphysics? In particular, what kind of natures or kinds of things could be its objects? And how precisely can an empirical concept such things be given without compromising the necessity required of the pure parts of natural science? Second, how is the special metaphysics provided by the Metaphysical Foundation supposed to be related to the transcendental part of the metaphysics of nature that was established in the Critique of Pure Reason? Does the former presuppose the principles of the latter, or are they logically independent but still related to each other in some other way? Another question concerns the method of special metaphysics. Is that method the conceptual analysis of the notion of matter, the transcendental investigation of the presuppositions of the mathematical science of nature, or something else entirely? First, Kant suggests that in special metaphysics, the principle of the transcendental part are applied to the two species of objects of our senses. Thus, particular kinds of things could only be investigated in a special metaphysics are the objects of outer senses, like matter, and objects of inner senses, like thinking beings, which would thus result in a doctrine of body and a doctrine of soul. Kant then argues that because the possibility of determinate natural things cannot be cognized from their mere concepts, it still requires that the intuition corresponding to the concept be given a priori, that is, that the concept be constructed, which is a task that requires mathematics. This is Kant's justification for his famous claim that in any special doctrine of nature, there can only be as much proper science as there is mathematics therein. This argument suggests the necessity required of a pure part of natural science derived from the necessity of the rules by which the mathematical construction of determinate things must proceed. Kant then uses the claim that science proper requires the construction of the concept of the object in the a priori intuition to exclude the possibility that chemistry and psychology, at least as they were practiced at the time, could count as science proper. In the case of chemistry, the problem is that no law of the approach of withdrawal of the parts of matter can be specified according to which their motions and all the consequences thereof can be made intuitive and presented a priori in space, a demand that will only with great difficulty ever be fulfilled. Since its principles are merely empirical, it can at least be a systematic art. The case of psychology is more complex since Kant provides at least two separate reasons in the preface for denying it the status of natural science proper. First, Kant claims that mathematics is inapplicable to the phenomena of an inner sense in their laws, though he grants the law of continuity ought to apply to changes in a representation as well. He downplays the significance of this application of the law of continuity, however, by noting that time has only one dimension, which does not provide enough material to extend our cognition significantly. Second, Kant also complains that empirical psychology cannot separate and recombine the phenomenon of inner self at will. Rather, our inner observation can be separated only by mere division in thought. Second, in examining how mathematics can be applied to bodies, Kant asserts that principles for the construction of the concepts that belong to the possibility of matter in general must first be introduced. Therefore, a complete analysis of the concept of matter in general must be provided in which makes use of no particular experiences, but only that which it finds in the isolated, although intrinsically empirical, concept itself in relation to the pure intuitions in space and time, and in accordance with laws that already essentially attach to the concept of nature in general. Kant then explains that this means that the concept of matter must be determined according to the critique of pure reasons, categories of quantity, quality, relation, and modality. Unfortunately, these points of clarification do not resolve all the issues that are immediately raised by Kant's pronouncements about what is required for natural science proper. So there's a lot of self-contradictions in Kant. So when we get to the Neo-Kantians kind of just accept that Kant contradicts himself, but has the most elaborate systematic view to build themselves off of, and aren't so worried about the internal contradictions in Kant, or say, what did he really mean? And he says this in one place and something else in another place. So I'm skipping that larger part of the scholarship, trying to deal with the various contradictions of what Kant says in different places in his own writings. For phoronomy, so let me put this up here. In case people have never seen this word. So Kant spells this differently. Phoronomy. Oh, sorry, I misspelled that. So phoronomy is the term used in Kant in Metaphysical Foundations of Natural Science for the study of motions of body without regard to forces of the nature of the bodies themselves, kinematics. So I don't think anyone else uses this term. I had to look this term up, so that's why I'm bringing it out here. Phoronomy is a term used in Kant and is referring to, I guess, kinematics or something. So I don't know if anyone in the chat or other people are familiar with this term. Phoronomy, I don't think it exists anymore as a proper term. The first chapter of the Metaphysical Foundations, the Phoronomy, considers the quantity of motion of matter and how it is to be constructed in intuition a priori, so as to produce the kind of rules that are necessary for our experience of matter in motion. Since extension and impenetrability are not directly relevant to how different magnitudes or degrees of motion can be represented. Kant restricts his discussion in this chapter to matter considered as a point, since the motion of a point in space can be represented straightforwardly. The main issue is how to represent the composition of two different motions. Kant's primary claim in this chapter is that due to the relativity of space, the fact that every motion can be viewed arbitrarily as either the motion of a body in a space at rest or as a body in a state of rest in a space which is motion in the opposite direction with the same velocity. The composition of two motions of one and the same point can only be thought in such a way that one of them is represented in absolute space, and instead of the other, a motion of the relative space with the same speed occurring in the opposite direction is represented as the same as the latter. So this is relatively complicated, and if like you do physics, you kind of do physics and you use an axis and you create an XY system and you decide which object you're going to put at the origin. But the metaphysics of what does that mean are actually extremely complicated. And they're to some extent there is no answer to it. So like for science and mathematics, how it's done versus what it means are somewhat divorced from themselves. And we'll see that Kant, to some extent, attempts to unify it, and later most scientists largely just divorce metaphysics from science. So Kant might be one of the last reasonable attempts at a unification of metaphysics and science. Until recently, very little has been written directly on Kant's Phoronomy. By contrast, Kant's philosophy of mathematics has long received considerable attention. Poulter, 1972, first broached the Phoronomy from a modern standpoint of coordinate transformations between frames. Friedman, 2013, untangles the complex strands of thought in Kant's chapter. His leading ideas for Kant's categories of quantity guarantee that motion is a magnitude, hence mathematics is applicable to the motions of bodies and kinematics. So it's an important topic for the conceptual for how science is done and calculated versus the metaphysics of what is actually happening. How do you understand that? Dynamics. The second chapter of Metaphysical Foundations, the dynamics, consider how it is possible to experience matter as filling a determinate region in space. So I'm leaving out most of this. Most of the stuff has largely been rejected or contradicts itself, but is important in the development of the history of philosophy of science. Kant thus directly confronts the metaphysical question of how to understand attraction that Newton attempted to avoid by positing it merely mathematically. As Kant interpreted the situation, Newton abstracts from all hypotheses purporting to answer the question as the cause of the universal attraction of matter, since the question is physical or metaphysical but not mathematical. In response to the most common objection to immediate action at a distance, namely that a matter cannot act immediately where it is not, Kant argues that action at a distance is no more problematic than action by contact, whether it is by collision or pressure, since in both cases a body is simply acting outside itself. Proposition 8 concludes by arguing that attractive forces act immediately to infinitely by adding a preliminary suggestion as to how one might be able to construct the concept of cohesion. And this will remain an extremely complicated topic to which there are many schools. So this question, action at a distance, or the nature of interaction from one body to another, will be a topic that currently recurs, and I would say presently there are multiple contradictory theories that still don't understand this topic. In the general remark to dynamics, Kant addresses two main issues. First, Kant considers how it is that specific varieties of matter might be reduced, at least in principle, to the fundamental forces of attraction and repulsion. The second issue concerns the fundamental distinction between the mathematical, mechanical, and the metaphysical dynamic mode of explanation. The former mode of explanation, which is associated with the postulation of atoms and the void, employs nothing more than the shapes and motion of fundamental particles and empty interstices interspersed among them. It contrasts with the metaphysical dynamic mode, which employs fundamental moving forces in its explanation. Kant grants that the mathematical mechanical mode has an advantage over the metaphysical dynamic mode, since its fundamental posits can be represented mathematically, whereas he repeatedly admits that the possibility of fundamental forces can never be comprehended. Their possibility can never be rendered certain. However, Kant thinks that this advantage is outweighed by two disadvantages. First, by presupposing absolute impenetrability, the mathematical mechanical mode of explanation attempts an empty concept at its foundation. Second, by giving up all forces that would be inherent in matter. Such a mode of explanation provides the imagination with more freedom that is truly consistent with the caution of philosophy. Given that the bulk of Kant's matter theory is presented in dynamics, it is unsurprising that it has received the greatest amount of attention in the literature. Friedman, 2013, an extensive commentary under the overarching theme that Kant in the dynamics aims to explain how certain features of body density, volume, static weight become mathematizable, as Newton's dynamic illustrates paradigmatically. Mechanics. The third chapter of Kant's metaphysical foundations, the mechanics, concerns how it is possible to experience matters having a moving force. That is, how one matter communicates its motion to another by means of its moving force. Kant begins in Proposition 1 by clarifying how the quantity of matter, is to be estimated before stating Propositions 2 to 4, three laws of mechanics. After first defining the quantity of matter and the quantity of motion, or in contemporary terms, impulse being mass times velocity, Kant asserts that the quantity of matter, in comparison with every other matter, can be estimated only by the quantity of motion at a given speed. Kant's proof proceeds by way of elimination. The quantity of matter, which is the aggregate of the movable in a determinate space, cannot be estimated by counting the number of parts it has, since, as was established in the dynamics, every matter is infinitely divisible. Nor can one estimate the quantity of matter merely by considering its volume, since different matter can have different specific densities. As a result, the only universally applicable way of estimating the quantity of matter is to hold the velocity of matter constant. Kant also asserts that the very possibility of natural science proper depends on the laws of inertia, since the rejection of it would be hylozoism, the death of all natural philosophy. In Remark 1, Kant then shows how his position differs from that of other authors. Newton by no means dared to prove this law a priori, and therefore appealed rather to experience. Kepler likewise derived it from experience, though he went further, conceiving of it in terms of special force of inertia. Certain unnamed transfusionists, presumably Locke and perhaps Cart and Roholt, attempted to deny the law altogether by suggesting that motion could simply be transferred from one body to another in the communication of motion. A view Kant rejects on the grounds that explaining the communication of motion in terms of transfer of motion is no explanation at all, and amounts to admitting that accidents could be literally transferred from one substance to another. Much of the modern tradition of scholarship used to regard Kant's laws of mechanics is derived from or even identical with Newton's three laws in the principle. Watkins, 1997, showed that Kant's formulation and justifications of his laws strongly influenced by a philosophy of nature stemming from Leibniz, not Newton. Stan, 2013, further corroborated these findings. As a result, it is safe to say Kant's foundation of the mechanics were significantly shaped by a post-Leibnizian rationalism too, not just Newton's mechanics. Phenomenology. The final chapter of the metaphysical foundations, the phenomenology, focuses on how the motion of matter can be experienced modally, that is, in terms of being possibly, actually, or necessarily in motion. In three propositions, specifically in accordance, Kant suggests with the results of three previous chapters, the rectilinear motion is merely possible predicate of matter, circular motion is an actual predicate of matter, and the equal and opposite motion of one matter with respect to another is a necessary motion of that matter. In the general remark to the phenomenology, Kant discusses the state of absolute space, which has been presupposed by the possible actual and necessary motion of matter at issue in the three main proposition, and explains that since it is not itself an object of experience, it must be represented by means of an idea of reason in Kant's technical sense of idea, namely as a concept for which a corresponding object could never be given to us by intuition. Though we can never know absolute space, it nonetheless functions as a regulative principle that guides us in our scientific practice by forcing us to look for further conditions for the conditioned objects we meet with experience. Kant's view that ideas of reason can function as regulative principles is developed in the appendix to the Transcendental Dialectic in the Critique of Pure Reason. Friedman's interpretation in 1992 of the phenomenology deserves special attention. According to him, in light of Kant's rejection of Newton's absolute space and time, he must give an actual account of the concept of true motion as change of true place over time presupposed by classical mechanics. To this end, Kant views the laws of motion as definite or constitutive of spatial temporal frameworks of Newtonian theory. Hence, these laws count as a priori for him. The reason Kant takes them as constitutive is the following. In Kant's phenomenology, the three Newtonian laws define a concept of true motion. The true motions of bodies just are those that obey the dynamic laws. Moreover, the concept must be given objective meaning and experience, measured empirically. To do so, Kant views Newton's three laws as holding primarily in a privileged system of reference, namely the center of mass frame of the system of the world, which the center of mass frame of our solar system approximates to a very good degree. Thus, by measuring the motion of bodies relative to this frame, we produce objective experience of those motions. However, the frame must first be located. To do so, Kant thinks we must likewise count the laws of universal gravitation as a priori, not empirical inductive. If we know a priori that all bodies in the solar system necessarily attract each other from their observably mutually induced accelerations, we can infer their masses. In turn, knowing their masses, we're able to locate the center of mass frame of the system. In a system of bodies, the center of mass is the point relative to which the body's distances are in inverse proportion to their masses. With respect to this distinguished frame, the motion of bodies count as their true motions. Friedman claims, hence, immediate and essential gravitation cannot be straightforwardly obtained from our experience of matter and its motion, but by some sort of inductive argument, say, because universal gravitation is necessarily presupposed in making an objective experience of matter and its motion possible in the first place. However, the center of mass frame of the solar system is just approximately an inertial frame. Scientific inquiry must ultimately look beyond it to better and better approximation of inertial frame, and Kant's absolute space is just the concept that directs our search for such approximations. More recently, Friedman updated and expanded his interpretation. In view of recent scholarship, Friedman has now made a convincing case that Kant's laws of mechanics, not Newton's three laws as claimed in 1992, that define the privileged frame, Kantian absolute space relative to which bodies have true motions in the phenomenology. Apart from Friedman's interpretation, there's relative secondary literature that discusses Kant's phenomenology. In physics, the post-critical period. Kant's interest in physics continued after the publication of the Metaphysical Foundations, in fact, until the very end of his productive years. Though Kant never completed a manuscript that could be put forward as a publication, the various notes, sketches, and drafts on topics in physics that he was working on intensively during this time were gathered together over a century after his death and published in his so-called opus posthumum. Despite the fragmentary nature, Kant made it clear that it is designed to fill an important gap in his system, just as Metaphysical Foundation had attempted to connect the transcendental principles of the Critique of Pure Reason and the principles that explain how matter is possible. The opus posthumum undertakes the task of effecting a transition from the special metaphysics of nature contained in Metaphysical Foundations to physics itself. However, Kant does not clarify adequately what systematic principles would guide this transition project, nor is it clear whether he takes the project to yield substantive principles or heuristic guidelines. On the one hand, in a note that stems from a period shortly after the publication of the Metaphysical Foundation, Kant suggests that one could follow the clue given by the categories and bring into play the moving forces of matter according to their quantity-quality relation and modality, a procedure that could be similar to the Metaphysical Foundation. On the other hand, in the Metaphysical Foundation already presupposes an imperial concept, namely matter, that transition to be carried out in the opus posthumum cannot be understood as moving from something non-empirical to something empirical. As Kant struggles with the problems that result from trying to account for now much of the specific features of matter, it is unclear that the categories are supposed to be of help in structuring Kant's argument. Thus, the precise argumentative structure of the opus posthumum remains problematic. Equally problematic is the exact nature of Kant's transition project, given his stated aim to account for specific features of matter, particular aggregation states, special forces. One would think that such contingent features are a problem for empirical science, not philosophy, since Kant sees the latter as pursuing knowledge that is, in various senses, necessary. Whatever its form, the content of Opus Posthumum includes reflections on a series of important topics in physics. 3 clusters are particularly noteworthy. Kant develops more detailed views about a number of outstanding issues concerning matter theory that he discussed, often in an attentive way, in the metaphysical foundations, such as fluidity, rigidity, cohesion, and the quantity of matter. Kant argues for the existence of an all-encompassing ether. This might seem to be natural development since metaphysical foundations was non-committal on the point, but what is surprising is that Kant thinks that the ether can be established a priori, which might seem to conflict with Kant's project in the Critique of Pure Reason. Kant also explores the idea that the subject must posit itself in positing the various forces of nature, a doctrine that has come to be known as Selbstsetzungslehr, and attempts to incorporate it into his views on how man is situated in between the world of experience and God, whose existence is a central requirement of morality. Okay, so we'll finish looking at Kant's views on biology, chemistry, and psychology. And these are actually going to become pretty important. And Kant's views on physics, to a large extent, are not applicable today anymore. Some of the metaphysics, it'll be important for the progression of these ideas in their current state, but kind of like Leibniz and Descartes and even Newton, if they had metaphysics, their metaphysics is largely no longer accepted. And even the physics itself was later canonized by Euler and Poincare and Hamilton and Laplace, and we'll talk about Lagrange, and we'll talk about that later also on future streams. Biology. Kant was interested not only in the inanimate bodies studied by physics, but also in the living organisms, which he viewed as deserving of additional philosophical scrutiny due to their special status for 2 reasons. First, the symmetries and regularities of their structure and workings make them in the highest degree contingent and mechanically inexplicable. Second, organisms come from their own kind, grow their own functional parts or organs, and repair them if they become damaged, and do and generally exhibit homeostasis. These facts about them prompt Kant to claim that an organism is cause and effect of itself. In a sense, a living entity is self-caused, and indeed by a causality that we can grasp solely under the idea of purposes as a principle. Organisms, in other words, are natural purposes or naturally occurring ensembles of parts purposely fitted and working in unity. In particular, he claims that attempting to explain organisms creates an inevitable conflict within reflective judgment, the faculty we employ in empirical concept formation, taxonomical classification, and the explanatory unification of particular laws. Kant describes the conflict in the antinomy of theological judgment. The antinomy obtains between 2 regulative principles, herein referred to by the R thesis and the R antithesis, to distinguish from 2 similar constitutive principles that Kant briefly discusses in the same place. R thesis: all generation of material things and forms must be judged as possible in accordance with merely mechanical law. Or R antithesis: some products of material nature cannot be judged as possible according to merely mechanical laws. Judging them requires entirely different laws of causality, namely that of final causality. A great deal of scholarship has aimed to elucidate this antinomy. First, clarification is needed about Kant's claim that organisms cannot be explained mechanically. In the Enlightenment, mechanical was used in at least 2 senses, broadly to denote explanations by physiochemical laws of efficient causation, and narrowly restricted to the theory of compound machines or assemblies of movable parts used to displace loads or transfer momentum, engines, and watches. McLaughlin, 1990, takes Kant to mean mechanical in the latter sense. In artificial machines, parts precede the whole temporally and determine it. The machine's configuration results from a summation over their parts, and its laws of operation are the same as those governing the parts. But organisms are different. The whole precedes its part, in organs and its functions, and aim-directed behavior is not present in them. Hence, organisms are mechanically inexplicable. Ginsburg, 2004, construes Kant's claims along different lines in two senses. According to one, to explain something mechanically is to show that its production results or would result from the unaided powers of matter. As such, Newtonian forces of attraction and repulsion and crude unorganized matter, or arbitrarily initial conditions such as masses, charges, configurations, and motions, organisms are inexplicable in the sense because their rising would be in the highest degree contingent. This is the notion operative in the antinomy of teleological judgment. Ginsburg contends, but she has argued there is a second, stronger sense. Not only are organisms inexplicable by reduction to the structure and powers of the organs, rather, their symmetries and regularities and powers are not explicable from the moving forces of their inorganic particles. Either organism-level powers are not vector sums or integrals of physiochemical forces that accelerate or reconfine subvisible particles. And I will return to the philosophy of biology eventually because I want to get to the hard problem of consciousness and the science of consciousness, which is based on biochemistry and biophysics. And so this question, is biology a science? And is chemistry a science, will become important. And then the teleological aspect of biology, although biology trying to portray itself as a science will try to remove theology from it. Chemistry. In the preface to the metaphysical foundation, Kant claims that chemistry, at least as he understood it in 1786, was not science proper, but such a claim leaves open the possibility that chemistry could be fully scientific in some other sense, or that with time it could develop into a proper science. Up through 1787, Kant accepted the fundamental tenets of Stahl's chemical theory, according to which water and air are fundamental elements that function as vehicles for change in both inflammable and earthy substances, as he commented on particular issues in chemistry in his various physical lectures. As a result, it is clear that Kant considers chemistry to be a science in some sense, even during the critical period. However, beginning in the mid-1780s and extending through the mid to late 1790s, Kant becomes aware of significant new developments in chemistry. In particular, Kant comes to reject Stahl's theory favoring Lavoisier's anti-phlogistic account of combustion and calcination, which relies on his doctrines of latent heat and caloric theory of the states of aggregation. While Kant never explicitly claims that chemistry so understood can be considered science proper, Kant's interest in these issues in the Opus Posthumum suggests that he was optimistic about providing the kind of foundation that would be required for it to attain this status. McNulty recently explained why Kant takes chemistry to miss the threshold for a proper science, specifically the sense in which chemistry is not mathematicisable in Kant's view. Psychology. Kant's view on psychology are immediately bound up with the more general position in the philosophy of mind. Still, one can take note of the fact that Kant distinguishes between rational and empirical psychology. In the Critique of Pure Reason, paralogisms, denies that rational psychology contains arguments that could justify any substantive principles, especially concerning our immortality. Thus, empirical psychology, it seems, could be possible as a science. However, Kant continues to maintain that science requires a pure part and denies the rational psychology contains any substantive knowledge that might constitute the pure part of psychology. Then it follows that empirical psychology cannot qualify as a science proper either. At the same time, Kant's own project in the Critique of Pure Reason requires that one might call transcendental psychology, that is, the study of those faculties that are required for us to have cognition. Transcendental psychology thus differs from rational psychology insofar as the former presupposes that we have experiences, albeit of a very general sort, whereas the latter is restricted to the mere concept "I think." Thus, it would seem that many of Kant's most important claims in the Critique of Pure Reason will fall under the domain of transcendental psychology. As is well known, Kant's Critique of Pure Reason came under attack immediately after its publication, most notably by Johann Georg Hamann, for not presenting an explicit account of how we obtain knowledge of our transcendental facilities. Just as Kant held that chemistry could either be scientific unless than the strictest sense, or perhaps becomes scientific proper depending on it develops. The same could be said for psychology. For one, Kant may simply be objecting to psychology as it was practiced in the 18th century based on introspection, a method that both rules out application in mathematics and gives rise to other difficulties. Further, in the critique of pure reason, Kant holds that although objects can never be given intuition that would correspond to ideas of reason, such ideas nevertheless function as regular principles that direct our understanding with regards to what should be inquire into next. Thus, our ideas of the world as a totality is supposed to drive us to look for similar and smaller parts to bodies and objects in further regions of space and in earlier moments of time. But if we have an idea of our soul, then it should too guide our scientific inquiry into our own representations, which seem to imply that psychology is a legitimate scientific practice, even if it does ultimately fall short of being science proper. Unsurprisingly, Kant influenced empirical theory in his 19th century Germany. However, it was his transcendental psychology and the critique of pure reason, not his views on empirical psychology, that proved the most influential. In particular, his doctrine of space and time as forms of sensibility was given a naturalistic construal in the physiology and psychology of perception. Since for Kant, an a priori form of intuition need not be innate, it could unfold in the course of sensory experience. This led Steinbuch, 1811, and Tortal, 1827, to investigate empirically how spatial representation arises, specifically how particular subjects become able to see things arrayed in space, perceive objects as three-dimensional, and represent spatial structures more generally. So psychology is a topic that I'm definitely going to return to more, possibly even more than science itself. And anyone who saw my essay on identity formation and theories of self, Kant is a major player in conceptions of self and a precursor to modern identity studies. So finally, history, very important. The other sciences, history, physical geography, and anthropology. Though Kant is sometimes quite strict about what qualifies as science proper, we've seen that he clearly accepts that other disciplines such as chemistry and psychology can be scientific in some sense. However, his explicit reflection about science extends even further, so as to include bodies of cognition such as history, physical geography, and anthropology. Even in the metaphysical foundation, Kant leaves room for such scientific cognition by dividing the doctrine of nature into natural science, like physics, and the historical doctrine of nature, which is separated further into natural descriptions and natural history. In the case of historical sciences, Kant views its cognitions as related not to subordination, as in the case of physics, but rather by coordination, since historical facts cannot be derived from each other, but rather merely related to each other in space geographically and time chronologically. Kant views anthropology as overlapping to some extent in the subject matter with empirical psychology. What enables the coordination of facts in each of these domains is not a theoretical, but rather a practical idea. In the case of history, it is the idea of reason or freedom that provides a guiding principle of coordination. Kant's idea of a universal history from a cosmopolitan point of view, while anthropology is framed by the cosmopolitan, more ideal of the world best. Thus, it is clear that Kant's emphasis on physics throughout his career did not blind him to the value of other science, nor did it keep him from reflecting creatively on how best to account for them in his perspective of his critical philosophy. Okay, there you have it. That was pretty long, and you went quite into detail on Kant, and we're going to see more of Kant. Like, Kant is not going away. Kant, like, if you're a Westerner trying to understand Western science, you can't escape Kant. It's very difficult. It's important. He pops up in countless fields and is a precursor in countless things that I'm researching, such as metaphysics, science, and especially psychology, self and identity formation, and the philosophy of mind, and the science of consciousness. And eventually, what we'll have to, for the science of consciousness, is really going to be the pinnacle of all of this, because the science of consciousness is going to be the interdisciplinary study of science, metaphysics, philosophy, theology, spiritualism, in various fields, because you see the limits of science, and also logic and mathematics. So I've already been going 4 hours, but I got more to do. Just pound forward, put the due diligence out there, public study session, show you what I'm working on. Just kind of reading these articles to practice my wording and to be able to conceptualize my thoughts within we'll call the canonical lexicon of the current science, and due diligence, so I'll be able to properly say ideas, and honestly this kind of just interests me. Honestly, like, I want to get this stuff right. I could put like some purpose, something I want to do with it. However, to some extent, I just want to understand the stuff. It just interests me. So let's look at finally the philosophy of technology. And it's going to be a big overview. I have engineering conferences coming up this summer. There's going to be a bunch of engineering conferences. Maybe starting in May, the Siemens conference is on Passover. I might have to miss the Siemens conference this year. But there's a bunch of conferences, Society of Automotive Engineering, another Automate conference, like the foam, cohesive, bonding, then the regular conferences I go to every year that will start popping up in the summer. So, I want to start taking my engineering more seriously, in the philosophy of science. And it's somewhat an interesting field, the overlay between the philosophy of engineering, because usually the philosophy of engineering is from the social sciences and the impact of technology and engineering on larger society, as opposed to the metaphysics and the connection between science and engineering. Because as I said, science has largely been divorced from technology. I mean, from metaphysics, that science is a method in what it produces. However, the proof of science is largely in the engineering, and then there's a connection to the truth of science because it works. And so most people don't really care about science. I mean, people like to know, well, why does that happen? Or, like understanding some phenomenon like the weather or the chemistry and physics of household appliances, running your house, various factors like air conditioning, heating, ventilation. I might also talk about the philosophy of architecture, but the science of our day-to-day life, to having some understanding of causal mechanisms versus being able to whip out like paper and pencil and mathematics and calculation. So, if it's just like a generic understanding, like, okay, you have a gas bill because your heater burns gas, and that or your automobile, versus actually being able to do calculations and mathematics and understand units, and like carbon dioxide and cycle and biology, versus things like computers. And you're saying, well, like for technology shows, to actually engineers who have to understand how these things work and design it, to other people who just use it. So I will be focusing on the philosophy of technology from the scientific end, not the cultural, sociological, and maybe a little bit economics. Sometimes when I go to the engineering shows, I talk a little bit about the economics. So let's jump right in. Philosophy of technology. And I will be skipping here the ethical components. The ethical components are important, but they're matter for a different discussion, and this is long enough without even covering any of the ethical components. But I don't want to diminish the importance of the ethics of technology. I'm just saying that time is limited. I've already been going for 4 hours now. Historical developments, the Greeks. Philosophical reflection on technology is about as old as philosophy itself. Our oldest testimony is from the ancient Greece. There are 4 prominent themes. One early theme is the thesis that technology learns from or imitates nature. According to Democritus, for example, house building and weaving were first invented by imitating swallows and spiders building their nests in nets, respectively. Aristotle referred to the tradition by repeating Democritus' example, but he did not maintain that technology could only imitate nature. Generally, techne, in some cases, completes what nature cannot bring to finish, and in other imitates nature. The second theme of the thesis is that there is a fundamental ontology distinction between natural things and artifacts. According to Aristotle, the former have their principles of generation and motion inside, whereas the latter, insofar as they are artifacts, are generated only by outward causes, namely human aims and forms of the human soul. Natural products, animals and their parts, plants and the four elements, move, grow, change, and reproduce themselves by inner final causes. They are driven by purpose of nature. Artifacts, on the other hand, cannot reproduce themselves without human care and intervention. They varnish after some time by losing their artificial form and decomposing into natural materials. For instance, if a wooden bed is buried, it decomposes into earth or changes back into its botanical nature by putting forth a shoot. The thesis that there is a fundamental difference between man-made products and natural substances has had a long-lasting influence. Aristotle's doctrine of the four causes, material, formal, efficient, and final, can be regarded as the third early contribution to the philosophy of technology. Aristotle explains this doctrine by referring to technical artifacts such as houses and statues. The four causes are still very much present in modern discussion related to the metaphysics of artifacts. Discussions of the notion of function, for example, focus on inherent teleological or final character and the difficulties this presents to its use in biology. In the notorious case of the ship of Theseus, identity over time, relative identity in sortals, was introduced in modern philosophy by Hobbes as showing a conflict between unity of matter and unity of form as principles of individuation. This conflict is seen by many as characteristics of artifacts. A fourth point that deserves mentioning is the extensive employment of technological images by Plato and Aristotle. In Timaeus, Plato describes the world as the work of an artisan, the demiurge. His account of the details of creation is full of images drawn from carpentry, weaving, ceramics, metallurgy, and agricultural technology. Aristotle used comparison drawn from the arts and crafts to illustrate how final causes are at work in natural processes, despite their negative appreciation of the life led by artisans who they consider too much occupied by the concerns of their professions and need to earn a living to qualify as free individuals. Both Plato and Aristotle found technological imagery indispensable for expressing their belief in the rational design of the universe. And the demiurge is one of Duvid's favorite topics, something I would like to return to later. In the realm of scholastic philosophy, there was an emergent application for the mechanical arts. They were generally considered to be born of and limited to the mimicry of nature. This view was challenged when alchemy was introduced in Latin West around the mid-12th century. Some alchemic writers, such as Roger Bacon, were willing to argue that human art, even if learned by imitating natural process, could successfully reproduce natural events or even surpass them. The result was philosophy of technology, in which human art was raised to a level of appreciation not found in other writings until the Renaissance. However, the last 3 decades of the 13th century witnessed an increasingly hostile attitude by religious authorities towards alchemy that culminated eventually in the denunciation written by the Inquisitor Nicholas Emeric in 1396. The Renaissance led to a greater appreciation of human beings and the creative efforts, including technology. As a result, the philosophical reflection on technology and its impact on society increased. Francis Bacon is generally regarded as the first modern author to put forward such reflection. His view, expressed in his fantasy New Atlantis 1627, was overwhelmingly positive. The positive attitude lasted well into the 19th century, incorporating the first half century of the Industrial Revolution. Karl Marx, for example, did not condemn the steam engine or the spinning mill for the vices of the bourgeois mode of production. He believed that ongoing technological innovation allowed for the necessary steps towards more blissful stages of socialism and communism of the future. During the last quarter of the 19th century, and most of the 20th century, a critical attitude predominated in philosophical reflection on technology. The representatives of this attitude were overwhelmingly schooled in the humanities and the social sciences, who had virtually no first-hand knowledge of engineering practice, whereas Bacon wrote extensively on the method of science and conducted physical experiments himself. Butler, being a clergyman, lacked such first-hand knowledge. Ernst Knapp, who was the first to use the term philosophy of technology in 1877, was a philologist and historian. Most of the authors who wrote critically about technology and its social cultural role during the 20th century were philosophers of general outlook such as Heidegger, Jonas, Galen, uh, Anders, and Feinberg. Others had background in one of the other humanities or in social science, such as literary criticism and social research in the case of Mumford, law in the case of Ellul, political science in the case of Winner, and literary studies in the case of Borgman. The form of philosophy of technology constituted by the writing of these and others has been called by Carl Mitchum, 1994, humanities philosophy of technology, because it takes the point of departure from the humanities and the social sciences rather than from the practices of science and engineering, and the approach is technology accepting the primacy of the humanities over technologies, since technology originates from the goals and values of humans. Humanities philosophers of technology tend to take the phenomenon of technology itself largely for granted. They treat it as a black box given, a unitary, monolithic, inescapable phenomenon. Their interest is not so much to analyze and understand the phenomenon itself, but to grasp it in relation to morality, politics, the structure of society, human culture, human condition, or metaphysics. In this case, these philosophers are almost all openly critical of technology. All things considered, they tend to have negative judgments on the way technology has affected human society and culture, or at least they single out for consideration the negative effects of technology on human society and culture. This does not necessarily mean that technology itself is pointed out as the principal cause of these negative developments. In the case of Heidegger, for particular, the paramount position of technology in modern society is rather a symptom of something more fundamental, namely a wrong-headed attitude toward being, which has been on the rise for almost 25 centuries. It is therefore questionable whether Heidegger should be considered as a philosopher of technology, although within the humanities view, he is considered to be amongst the most important ones. Much the same could be said about Hannah Arendt, in particular her discussion on technology in the human condition, 1958, although her position in the canon of humanities, philosophy of technology, is not as prominent as Heidegger's. Okay, Conway, thanks for tuning in. Appreciate it. God bless. Have a great night. See you next time. In his development, humanities' philosophy of technology continues to be influenced not so much by development in philosophy, but by developments in the social sciences and humanities. Basic ambiguity in the meaning of technology. Mitchum contrasts humanities' philosophy of technology to engineering philosophy of technology, where the latter refers to philosophical views developed by engineers or technologists as attempts to elaborate a technological philosophy. Mitchum discusses only a handful of people as engineering philosophers of technology. Ernst Knapp, Paul Engermeyer, Friedrich Dessauer, and more briefly Jacques Lafitte, Gilbert Simondon, Hendrik van Riesen, Juan David Garcia Baca, Buckminster Fully, and Mario Bunge. The latter, the label engineering philosophy of technology raises serious questions. Many of the persons discussed hardly classify as engineers or technologists. It is also not very clear how the notion of a technological philosophy should be understood. As philosophers, these authors seem all to be rather isolated figures whose work show little overlap or seem to be sharing mainly the absence of a working relation with established philosophical disciplines. It is not so clear what sorts of questions and concerns underlie the notion of engineering philosophy of technology. A crucial role for a systematic philosophy could bring it quite close to some examples of humanities' philosophy of technology, for instance, the work of Jacques Ellul, where the analysis would be rather similar to the remaining differences would be ones of attitude and appreciation. And seeing technology is grounded in a practice sustained by engineers, similar to the way philosophy of science focuses on the practice of science as sustained by scientists, analytic philosophies of technology could be thought to amount to the philosophy of engineering. Indeed, many of the issues related to design could be singled out as the forming of the subject matter philosophy of engineering. The metaphysical issues, however, and analytical philosophy of technology is therefore significantly broader than the philosophy of engineering. The very title of philosophy of technology and engineering sciences, an extensive up-to-date overview, which contains contributions to all the topics treated in the next section, suggests that technology and engineering do not coincide, but the book does not specifically address what distinguishes technology from engineering and how they are related. In fact, the existence of humanities philosophy of technology and analytical philosophy of technology next to one another reflects a basic ambiguity in the notion of technology that the philosophical work that has been going on has hardly succeeded in clarifying. Technology can be said to have two aspects or dimensions, which can be referred to as instrumentality and productivity. Instrumentality covers the totality of human endeavors to control their lives and their environments by interfering with the world as an instrumental way by using things in a purposeful and clever way. Productivity covers the totality of human endeavors to bring into existence new things through which certain things can be realized in a controlled and clever way. For the study of the dimension of instrumentality, it is in principle irrelevant whatever the things that are made use of in controlling our lives and environments have been produced by us first. If we somehow could rely on natural objects to always be available to serve our purposes, the analysis of instrumentality and its consequences for how we live our lives would be not necessarily be affected. Likewise, for the analysis of what is involved in the making of artifacts and how the notion of an artifact and of something new being brought into existence are to be understood, it is to a large extent irrelevant how human life, culture, and society are changed as a result of the artifacts that are in fact produced. Notwithstanding this fundamental character, the ambiguity noted here seems hardly to be confronted directly in the literature. Humanities philosophy of technology has been interested predominantly in the instrumentality dimension, whereas analytical philosophy of technology is focused on the productivity dimension. But technology is one of the basic phenomena of modern society, if not the most basic one, clearly constituted by the process centering on and involving both dimensions. It has proved difficult, however, to come to an overarching appreciation in which the interaction between the two dimensions of technology are adequately dealt with. No doubt, partially due to the great differences in philosophical orientation and the methodology associated with the two traditions and their separate foci. To improve the situation is arguably the most urgent challenge that the field of philosophy of technology as a whole is facing, since the continuation of the two orientation leading to their separate lives threatens its unity and coherence as a discipline in the first place. Indeed, during the past 10 to 15 years, the philosophy of engineering has established itself as a subdiscipline within the philosophy of technology. Analytical philosophy of technology. Science and technology's different relation to philosophy. It may come as a surprise to those new to the topic that the fields of philosophy of science and philosophy of technology show such great differences, given that few practices in our society are as closely related as science and engineering. Experimental science is nowadays crucially dependent on technology for the realization of its research setups and the gathering and analyzing data. The phenomenon that modern science seeks to study could never be discovered without producing them through technology. Theoretical research within technology has come to often be indistinguishable from theoretical research in science, making engineering science largely continuous with ordinary pure science. This is a relatively recent development which started around the middle of the 19th century and is responsible for great differences between modern technology and traditional craft-like techniques. The educational training that aspiring scientists and engineers receive starts off being largely identical and only gradually diverges into a science or an engineering curriculum. Ever since the scientific revolution of the 17th century, characterized by its two major innovations, the experimental method and the mathematical articulation of scientific theories, philosophical reflection on science is focused on the method by which scientific knowledge is generated, on the reasons for thinking scientific theories to be true or approximately true, and on the nature of evidence and the reasons for accepting one theory and rejecting another. Hardly ever have philosophers of science posed questions that did not have the community of scientists, their concerns, their aims, their intuitions, their arguments and choices as a major target. In contrast, it is only recently that the philosophy of technology has discovered the community of engineers. It might be claimed that it is up to the philosophy of technology and not the philosophy of science to target first all the impact of technology and with it science on society and culture, because science affects society only through being applied as technology. This, however, will not do. Right from the start of the scientific revolution, science affected human culture and thought fundamentally and directly, not with a detour through technology, and the same is true for later developments such as relativity, atomic physics, and quantum mechanics, the theory of evolution, genetics, biochemistry, and the increasingly dominating scientific worldview overall. All the same philosophers of science for a long time gave the impression that they left questions addressing the normative social and cultural aspects of science gladly to other philosophical disciplines or to historical studies. There is a major difference between the historical development of modern technology as compared to modern science, which may at least partly explain this situation, which is that science emerged in the 17th century from philosophy itself. The answer that Galileo, Huygens, Newton, and others gave, by which they initiated the alliance of empiricism and mathematical description that is so characteristic of modern science, were answers to questions that belonged to the core business of philosophy since antiquity. Science, therefore, kept the attention of philosophers. Philosophy of science can be seen as a transformation of epistemology in light of the emergence of science. The foundational issue, the reality of atoms, the status of causality, the probability, questions of space and time, the nature of the quantum world, that were so lively discussed during the end of the 19th and the beginning of the 20th century are an illustration of the close relationship between scientists and philosophers. Not so much intimacy has ever existed between philosophers and engineers or technologists. Their worlds still barely touch. To be sure, a case can now be made compared to the continuity existing between natural philosophy and science. A similar continuity exists between central questions in philosophy having to do with human action and practical rationality, and the way technology approaches and systematizes the solution of practical problems. The relationship between technology and science. The close relationship between the practices of engineering and science may easily keep the important differences between the technology and science from view. The predominant position of science as the philosophical field of vision made it difficult for philosophers to recognize that technology merits special attention for involving issues that do not emerge in science. This view resulting from this lack of recognition is often presented, perhaps somewhat dramatically, as coming down to a claim that technology is merely applied science. The questioning of the relationship between science and technology was the central issue in one of the earliest discussions among analytical philosophers of technology in 1966 in a special issue of the journal Technology and Culture. Henryk Skolimowski argued that technology is something quite different from science. As he phrased it, science concerns itself with what is, whereas technology concerns itself with what is to be. A few years later, in his well-known book, The Science of the Artificial, 1969, Herbert Simon emphasized this important distinction in almost the same words, stating that the scientist is concerned with how things are, but the engineer is how things ought to be. Although it is difficult to imagine that earlier philosophers were blind to the differences in orientation, their inclination, in particular, in the tradition of logical empiricism, to view knowledge as a system of statements, may have led to a conviction that in technology, no knowledge claims play a role that cannot also be found in science. The study of technology, therefore, was not expected to pose new challenges nor hold surprises regarding the interest of analytical philosophy. In contrast, Mario Bunge, 1966, defended the view that technology is applied science, but in a subtle way that does justice to the differences between science and technology. Bunge acknowledged that technology is about action, but an action heavily underpinned by theory. That is what distinguishes technology from arts and crafts and puts it on par with science. According to Bunge, theories of technology come in two types: substantive theories, which provide knowledge about the object of action, operative theories, which are concerned with action itself. The substantive theories of technology are indeed largely applications of scientific theories. The operative theories, in contrast, are not preceded by scientific theories, but are born in applied research itself. Still, Bunge claims operative theories show a dependence on science in that in such theories, the methods of science is employed. This includes such features as modeling and idealization, the use of theoretical concepts and abstractions, and the modification of theories by the absorption of empirical data through prediction and retrodiction. In response to this discussion, Ian Jarvie, 1966, proposed an important question For a philosophy of technology, what is epistemological status of technology statements, and it's how technological statements are to be demarcated from scientific statements. This suggests a thorough investigation of the various forms of knowledge occurring in either practice. In particular, since scientific knowledge has already been so extensively studied of the forms of knowledge that are characteristic of technology and are lacking or of much less prominence in science. A distinction between knowing that traditional proposition knowledge and knowing how non-articulated and even impossible to articulate knowledge had been introduced by Gilbert Ryle in 1949 in a different context. The notion of knowing how was taken up by Michael Polanyi under the name of tacit knowledge and made central characteristic of technology. The current state of the philosophical discussions is presented in this encyclopedia's entry on knowledge how, however, emphasizing too much the role of unarticulated knowledge or rules of thumb, as they've often been called, easily underplays the importance of the rational methods in technology. An emphasis on tacit knowledge may also be ill fit for distinguishing the practices of science and engineering, because the role of tacit knowledge in science may well be more important than current philosophy of science acknowledges. For example, in concluding causal relations on the basis of empirical evidence, this was also an important theme in the writings of Thomas Kuhn on theory change in science. Centrality of design to technology. To claim with Skolimowski and Simon that technology is about what is to be or what ought to be rather than what is may serve to distinguish it from science, but will hardly make it understandable why so much philosophical reflection on technology has taken the form of social cultural critique. Technology is an ongoing attempt to bring the world closer to the way one wishes it to be, whereas science aims to understand the world as it is. Technology aims to change the world. These are abstractions, of course, for one whose wish concerning what the world should be like are realized in technology. Unlike scientists who are often personally motivated in their attempts at describing and understanding the world, engineers are seen not in the least by engineers themselves as undertaking their attempts to change the world as a service to the public. The ideas on what it is to be or what ought to be are seen as originating outside of technology itself. Engineers then take it upon themselves to realize these ideas. This view is a major source in the widely spread picture of technology as being instrumental, as delivering instruments ordered from elsewhere as a means to ends specified outside of engineering, a picture that is served further to support the claim that technology is neutral with respect to values. This view involves a considerable distortion of reality. However, many engineers are intrinsically motivated to change the world, in particular the world as shaped by past technology. As a result, much technological development is technology driven. To understand where technology comes from, what drives the innovation process, is of importance not only to those who are curious to understand the phenomenon of technology itself, but also to those who are concerned about its role in society. Technology or engineering as a practice is concerned with the creation of artifacts and increasing importance, artifact-based services. The design process, the structured process leading towards the goal forms the core of the practice of engineering. In the engineering literature, the design process is commonly represented as consisting of a series of translational steps at the start of the customer's needs or wishes. In the first step, these are translated into a list of functional requirements, which then define the design task an engineer or team of engineers has to accomplish. The functional requirements specify as precisely as possible what the device to be designed must be able to do. This step is required because customers usually focus on just one of the two features and are unable to articulate the requirements that are necessary to support the functionality they desire. In the second step, the functional requirements are translated into design specifications, which the exact physical parameters of crucial components by which the functional requirements are going to be met. The design parameters chosen to satisfy these requirements are combined and made more precise by such a blueprint of the device results. The blueprint contains all the details that must be known, such as the final step of the process or of manufacturing the device can take place. It is tempting to consider the blueprint as the end result of the design process instead of a finished copy being this result. However, actual copies of the device are crucial for the purpose of prototyping and testing. Prototyping and testing presuppose the sequence of steps making up the design process can and will often contain iterations leading to revisions on the design parameters and of the functional requirements. Even though certainty for mass-produced items, the manufacturer of a product for delivery to its customers or to the market after the closure of the design phase. The manufacturing process is often reflected in the functional requirements of a device. For example, in putting restrictions on the number of different components of which the device consists, the complexity of a device will affect how difficult it will be to maintain or repair it, and ease of maintenance or low repair cost are often functional requirements. An important modern development is that the complete life cycle of an artifact is now considered to be the designing engineers concerned up to the final stages of the recycling and disposal of the components and materials, and the functional requirements of any device should reflect this. From this point of view, neither a blueprint nor a prototype can be considered the end product of an engineering design. The biggest idealization of the scheme of the design process contained is arguably located in the start. Only a minority of cases does a design task originate in a customer need or wish for a particular artifact. First of all, as already suggested, many design tasks are defined by engineers themselves, for instance, by noticing something to be improved in existing products. Nevertheless, design often starts with a problem pointed out by some societal agent, which engineers are then invited to solve. Many such problems, however, are ill-defined or wicked problems, meaning that it is not at all clear what the problem is exactly and what a solution to the problem would consist in. The problem is the situation that people, not necessarily the people in the situation, find unsatisfactory, but typically without being able to specify a situation that they find more satisfactory in other terms than as one in which the problem has been solved. In particular, it is not obvious that a solution to the problem would consist in some artifact or some artifactual system or process being made available or installed. Engineering departments all over the world advertise that engineering is a problem solving, and engineers easily seem confident that they are best qualified to solve a problem when they are asked to, whatever the nature of the problem. This has led to the phenomenon of a technological fix, the solution of a problem by a technological solution, that is, the delivery of an artifact or artifactual process where it is questionable, to say the least, whether this solves the problem as to whether it was the best way of handling the problem. These wicked problems are often broadly social problems, which would best be met by some form of social action, which would result in people changing their behavior or acting differently in such a way that the problem would be mitigated or even disappear completely. In defense of the engineering view, it could perhaps be said that the repertoire of proven forms of social action is meager. The temptation of technological fixes could be overcome, at least that is how an engineer might see it, by the inclusion of the social sciences in the systematic development and application of knowledge to the solution of human problems. This, however, is a controversial view. Social engineering is to many a specter to be kept as at a large a distance as possible instead of an ideal to be pursued. Karl Popper referred to acceptable forms of implementing social change as piecemeal social engineering and contrasted it to revolutionary but completely unfounded schemes advocating by such Marxism. In the entry on Karl Popper, however, his choice of words is called rather unfortunate. The notion of social engineering and its cogency deserves more attention than it currently receiving. An important input for the design process is scientific knowledge, knowledge about the behavior of components and the materials they are composed of in specific circumstances. This is the point where science is applied. However, much of this knowledge is not directly available from the sciences, since it is often concerns extremely detailed behavior in very specific circumstances. The scientific knowledge is therefore often generated within technology by the engineering sciences. But apart from this very specific scientific knowledge, engineering design involves various other sorts of knowledge. In his book, What Engineers Know and How They Know It, Vincenti, 1990, the aeronautical engineer Walter Vincenti gave a six-fold categorization of engineering design knowledge, leaving aside production and operation as the other two basic constituents of engineering practice. Vincenti distinguishes: one, fundamental design concepts, including primarily the operational principle and the normal configurations of a particular device; two, criteria and specifications; three, theoretical tools; four, quantitative data; five, practical considerations; six, design instrumentalities. The fourth category concerns the quantitative knowledge just referred to, and the third, the theoretical tools used to acquire it. These two categories can be assumed to match Bunge's notion of substantial technological theories. The status of the remaining four categories is much less clear, however, partly because they are less familiar or not at all from the well-explored context of science. Of these categories, Vincenti claims that they represent prescriptive forms of knowledge rather than descriptive ones. Here, the activity of design introduces an element of normativity which is absent from scientific knowledge. Take such a basic notion as operational principle, which refers to the way in which the function of a device is realized, or in short, how it works. This is still a purely descriptive notion. Subsequently, however, it plays a role in arguments that seek to prescribe a course of action to someone who has a goal that could be realized by the operation of such a device. At this stage, the issue changes from a descriptive to a prescriptive or normative one. An extensive discussion of the various kinds of knowledge relevant to technology is offered by Hooks 2009. Although the notion of an operational principle, a term that seems to originate with Polanyi 1958, is central to engineering design, no single clear-cut definition of it seems to exist. The issue of disentangling descriptive from prescriptive aspects is an analysis of technical actions and their constituents is therefore a task that had hardly begun. This task requires a clear view on the extent and scope of technology. If one follows Joseph Pitten's book, Thinking about Technology, 1999, and defines technology broadly as humanity at work, then to distinguish between technical action and action in general becomes difficult, and the study of action in technology must absorb all descriptive and normative theories in action, including the theory of practical rationality and much of the theoretical economics in its wake. There have been indeed attempts at such an encompassing account of human action. For example, Kordobinsky's Praxeology, 1965, but a perspective of such generality makes it difficult to arrive at results of sufficient depth. It would be a challenge for philosophers to specify the differences among action forms and the reasoning grounding them in, to single out three prominent fields of study: technology, organization and management, and economics. A more restrictive example at such is an approach, 1993, Nino Luato. According to Nino Luato, the theoretical framework of technology as an activity that is concerned with what the world should be like rather than it is. The framework that forms the counterpoint to the descriptive framework of science is design science. The content of design science, the counterpoint to the theories and explanations that form the content of descriptive science, would be then formed by technical norm statements of the form, if one wants to achieve X, one should do Y. This notion of technical norms derives from George Henrik von Wright's Norms in Action, 1963. Technical norms need to be distinguished from an acoustic statement expressing natural necessity in the form of, if X is to be achieved, Y needs to be done. The latter have a truth value, but the former have not. Von Wright himself, however, wrote that he did not understand the mutual relationship between these statements. Methodological issues, design, and decision making. Design is an activity that's subject to rational scrutiny, but in which creativity is considered to play an important role as well. Since design is a form of action, structured series of decisions to proceed in one way rather than another, the form of rationality that is relevant to it is practically rational, the rationality incorporating the criteria of how to act given particular circumstances. This suggests a clear division of labor between the part to be played by rational scrutiny and the part to be played by creativity. Theories of rational action generally conceive the problem situation as one involving a choice among various courses of action open to the agents. Rationality then concerns the question how to decide among given options, whereas creativity concerns the generation of these options. This distinction is similar to the distinction between the context of justification and the context of discovery in science. The suggestion that is associated with this distinction, however, that rational scrutiny only applies in the context of justification, is difficult to uphold for technological design if the initial creative phase of option generation is conducted sloppily. The result of the design task can be handled hardly be satisfactory, unlike in the case of science, where the practical consequences of entertaining a particular theory are not taken into consideration. The context of discovering technology is governed by severe constraints in time, money, and the analysis of the problem how to best proceed certainly seems in order. The ideas of Herbert Seidman on bounded rationality, 1982, are relevant here since decisions on when to stop generating options and when to stop gathering information about these options and the consequences when they are adapted are crucial in decision making, and information overload and calculative interactability are to be avoided. However, it has proven difficult to further develop Simon's ideas on bounded rationality since their conception in the 1950s. Another notion is that it is relevant here is means ends reasoning. In order to be of any help here, theories of means end reasoning should then concern not just the evaluation of given means with respect to their ability to achieve given ends, but also the generation of construction of means for given ends. When engineering design is conceived as a process of decision making governed by considerations of practical rationality, the next step is to specify these considerations. Almost all theories of practical rationality conceive of it as a reasoning process where a match between beliefs and desires or goals is sought. The desire or goals are repeated by their value or utility for the decision maker, and the decision maker's problem is to choose an action that realizes a situation that ideally has maximal value or utility among all the situations that could be realized. If there is uncertainty concerning the situations that will be realized by a particular action, then the problem is conceived as aiming for maximal expected value or utility. Now, the instrumental perspective on technology implies that the value that is at issue in the design process, viewed as a process of rational decision making, is not the value of the artifacts that are created. Those values are the domain of the users of the technology so created. They are supposed to be represented in the functional requirements defining the designing task. Instead, the value to be maximized is the extent to which a particular design meets the functional requirements defining the design task. It is in this sense that engineers share an overall perspective on engineering design as an exercise in optimization. But although optimization is a value oriented notion, it is not itself perceived as a value driving engineering design. Metaphysical issues, the status and characteristics of artifacts. Understanding the process of designing artifacts is the theme in philosophy of technology that most directly touches on the interest of engineering practice. This is hardly true for another issue of central concern to analytical philosophy of technology, which is the status and the character of artifacts. This is perhaps not unlike the situation in the philosophy of science, where working scientists seem also to be much less interested in investigating the status and character of models and theories than philosophers are. Artifacts are man made objects, they have an author. These artifacts that are of relevance to technology are additionally made to serve a purpose. This excludes with a set of all man-made objects, byproducts and waste products, and equally though controversially works of arts. Byproducts and waste products are results from an intentional act to make something, but just not precisely, although the author at work may well be aware of their creation. Works of art result from an intentional directed at their creation, although in exceptional cases of conceptual art, this directness may involve many intermediate steps, but it is contested whether artists include in their intention concerning their work an intention that the work serves some purpose. Nevertheless, most philosophers of technology who discuss the metaphysics of artifacts exclude artwork from their analysis. Technical artifacts then are made to serve some purpose, generally to be used for something or to act as a component in a larger artifact, which in its turn is either something to be used or, again, a component. Whether end product or component, an artifact is for something, and what it is for is called the artifact's function. Several researchers have emphasized that an adequate description of artifacts must refer both to their results as tangible physical objects and to the intention of the people engaged with them. Croce and Mayers, 2006, have dubbed this the dual nature of technical artifacts. It is most mature formulation. They suggest that two aspects are tied up, so to speak, in the notion of artifact function. This gives rise to severe problems. One which would be passed over quickly because little philosophical work seems to have been done concerning it is that structure and function mutually constrain each other, but the constraining is only partial. It is unclear whether a general account of this relation is possible and what problems need to be solved to arrive there. There may be interesting connections with the issue of multiple realizability in the philosophy of mind and with accounts of reduction in science. It is equally problematic whether a unified account of the notion of function as such is possible, but this issue has received considerably more philosophical attention. The notion of function is of paramount importance for characterizing artifacts, but the notion is used much more widely. The notion of an artifact functioning seems to refer necessarily to human intentions. Function is also a key concept in biology. However, where no intentionality plays a role, it is a key concept in cognitive science and the philosophy of mind. where it is crucial in grounding intentionality in non-intentional structure and physical properties. Up till now, there is no accepted general account of function that covers both the intentionality-based notion of artifact function and the non-intentional notion of biological function, not to speak of the other areas where the concept plays a role, such as the social sciences. Again, against the view that, at least in the case of artifacts, the notion of a function refers necessarily to intentionality, it could be argued that in discussing the functions of the components of a larger device and the interrelations between these functions, the intentional side of these functions is of secondary importance only. This, however, would only be to ignore the possibility of the malfunctioning of such components. The notion seems to be definitely only in terms of a mismatch between the actual behavior and intended behavior. The notion of malfunction also sharpens an ambiguity in the general reference to the intentions when characterizing technical artifacts. These artifacts usually engage many people, and the intention of these people may not all pull in the same direction. A major distinction can be drawn between the intentions of the actual users of an artifact for a particular purpose and the intention of the artifact's designer. Since an artifact may be used for a purpose different from the one for which the designer intended to be used, and since people may also use natural objects for some purpose or other, or is invited to allow that artifacts can have multiple functions, or to enforce a hierarchy among all relevant intentions in determining the function of an artifact, or to introduce a classification of function in terms of the sorts of determining intentions. In the latter case, which is a sort of middle way between the two other options, one commonly distinguishes between proper function of an artifact as the one intended by the designer and accidental function of the artifact as the one given to it by some user on private considerations. Accidental can become so common, however, that the original function drops out of memory. Close related to the issue to what extent use and design determine the function of an artifact is a problem of characterizing artifact kinds. The distinction between artifact kinds and functional kinds is relevant to the status of such kinds in comparison to other notions of kinds. Philosophy of science has emphasized that the concept of natural kind, such as exemplified by water or atom, lies at the basis of science. On the other hand, generally taken for granted that there are no regularities that all knives or airplanes or pistons answer to. This, however, is loosely based on the consideration of multiple realizability that fully apply to functional kinds, not to artifact kinds. Artifact kinds share an operational principle that gives them some commonality in physical features, and this commonality becomes stronger once a particular artifact kind is subdivided into narrow kinds. Since these kinds are specified in terms of physical and geometric parameters, they are much closer to the natural kinds of science in that they support law-like regularities. Okay, so there you have it, folks. I'm going to skip the ethical applications of technology. That's probably the more commonly, as said, there's not a well-developed scientific study of technology. The main application now is the general sociological, philosophical study of technology, and a lot of that focuses on the ethics of technology. As an engineer, there's training in design processes, how to be a good engineer, but not necessarily framed in the conception of philosophy of engineering. So almost 5 hours here. So, got to rest my voice. I actually might do quite a few of these. I might even do 5 to 10 of these. Kind of putting out my own research, to listen back and just get my mouth used to expressing these concepts in a canonized form, reading through these documentations. I'm reading a lot of books. I'm reading a lot of the source literature, a lot of these names like Week in Review. So a lot of these names that, you're seeing quoted as sources, we've been talking about, and I've been sharing some of their literature on Week in Review. So, maybe this will benefit Week in Review to be able to drive further progress to the people that really want, seen as like an adjunct to Week in Review, to people who want to go more in depth on these topics, kind of do it like a book on tape. They could listen to me reading these articles. You could, read along with them also, and hopefully, Week in Review will discuss them more. And moving forward to eventually advance my own ideas that they're, to do the due diligence, like, for published, like I'm not going to go to the Science of Consciousness conference this year. It didn't work out that way. I'd wanted to go to the Science of Consciousness conference maybe next year, if I were to write, like I talked about the scientific method and peer review and publishing, to do the due diligence to publish a scientific paper. And that means the historical review, the current state of knowledge, and building upon the current state of knowledge, that I have a comprehensive understanding of what is the current state of knowledge and how am I pushing forward the current state of knowledge. Okay, Nam, you stayed in the whole time. Appreciate that. So probably Sunday, if I have the strength, I'm going to try to do these on Sundays and Wednesdays. So I'll try to stream 2 times a week, and hopefully to finish before Passover. So I have a whole bunch of articles. I want to get into, maybe the next stream, I'm going to cover neo-Kantianism. I'm going to go more into various concepts of the structure of scientific theory, scientific explanations, and model theory, like I covered here in scientific explanation. So I'm going to go much more into detail in what is a scientific model, what are the various theories of scientific models, in relationship to multiple truth hypothesis. That would get into the metaphysics of truth, some like theories of logic and truth value estimation. How do you look at a functioning model or conflicting functioning models of technology? I'm going to go more into Kant and Hume. I'm going to cover neo-Kantianism and the Vienna Circle. So anyone who's familiar with science, like Einstein arises from the Vienna Circle, but 2 of the major schools leading into the philosophy of science into the quantum revolution are the neo-Kantians of the Marburg School and the Vienna Circle. So I'm going to, probably next time, I'll maybe cover the neo-Kantianism and the Marburg School. I might cover a little bit more about Hume and Kant. I might go a little more detail into Hume and Kant. And from there, I'm going to move into things like logical empiricism, Einstein's theory of science, computational philosophy, possibly covering like neuroscience and biology, like the epistemological, metaphysical background for the various sciences. And then eventually we're going to get into the actual science, like, because I want to move into the science of consciousness, the hard problem of consciousness. So there's a lot of prerequisite materials, because the science of consciousness is to some extent the pinnacle of all wisdoms. You need to understand biology, chemistry, physics, even quantum physics, mathematics, logic, and then metaphysics, spiritual aspects, and some sort of grand unification, psychology. So there's a lot of material to cover. But next time I'll probably continue after Kant with like the neo-Kantianism and the Vienna School of the philosophy of science, and maybe logical empiricism, and go into more details about what is models. I also have like the philosophy of measurement and theoretical terms, mechanisms. It's really an endless topic. So I said, like, it could just go on and on and on. So, we'll see. Yeah, I mean, even like if you're referring to Vedic terminology, I would like to cover that also. Although for the first, probably like a full 5 streams are going to fully focus on, so to say, dead white men and the European conception of the modern state of science. I want to get that fully conceptualized. But yeah, then I do want to bring in other things. And I'm not an expert, but yeah, I would like to bring in Hindu conceptions, Eastern conceptions, Kabbalistic and other insights, metaphysics. And I'm eventually going to get back to dualism. So when I get to philosophy of mind and the hard problem of consciousness, I'm going to be returning to the metaphysics. And the whole purpose of me going so in depth into the philosophy of science is to show that science only loosely informs metaphysics and the boundary of science, that science cannot explain consciousness, and then how to interplay if science is divorced from metaphysics. How do you give a metaphysical conception of the philosophy of mind within a scientific framework? And that's really the standstill right now of the hard problem of consciousness, where there's the expectation of the scientific method to provide answers to these questions of mind and consciousness, and the inability of the scientific method to have substantial breakthroughs in consciousness. And you're kind of like Jennifer, like studying physics for credibility in the West. So I really have to go through the full gamut of scientific knowledge to show what science actually says, so that I could definitively say science does not say this. And so it's your really extensive due diligence to give spiritual, metaphysical interpretations of psychology, of philosophy of mind, of the science of consciousness. I have to definitively show the boundaries of science. And so therefore it's going to be a long path, and I probably have like a full at least 5 videos just on the Western conception of science, and I want to take it up to the present day, which means quantum mechanics. And when I talk about the multiple truth hypothesis, the multiple truth hypothesis closest parallels are actually in theoretical physics, in like the multiverse, in the holographic universe, and various concepts like that. So part of my intention here also is to get to the modern scientific conception of these extremely complicated ideas like the holographic universe and the multiverse. And I covered that briefly and read some of Max Tegmark's in the first programs I did on the multiple truth hypothesis. But I want to fully ground these concepts. Why are things like the multiverse and holographic universe coming up as scientific theories? And it comes back to this unification of metaphysics and science to, at a certain point, like after Kant, and some of the neo-Kantians, science became divorced from metaphysics and philosophy into its own subject. But in order to answer the hard problem of consciousness, there has to be some sort of reconciliation between science, metaphysics, philosophy, theology, and like the T-jump, kind of like science answers everything, and theology is no longer useful because science has replaced it. So I really like it, and I'm not anti-science, I'm pro-science. I just think that science only covers certain useful aspects, and therefore I have to really cover the whole gamut of the philosophy of science and the broad scope of science in order to define its boundaries, so I can come back in to where these other metaphysical, theological concepts are going to be useful. And then also I have these I think I mentioned Swedenborg. All these names are hard to keep in my mind, so just reading these out, doing these streams, because like they're like science, even the philosophy of science, the history of science, like I was mentioning, like Pierre Duhem the other day. So there is the Duhem-Gibbs hypothesis. If you're like take physics, maybe you've heard like Duhem. But even just within the laws of science and mathematics, there's thousands and thousands of names. There's new discoveries like mathematical, physical theories. If you're in engineering, there's like your neurology. Every year, there's new names that discover theories. And just to keep track of all of these names, and a lot of these theories use conflicting models. And that's where the multiple truth hypothesis will be useful just in the field of science itself. So like in the conception of a scientific model that explains some phenomenon but not others, and another scientific model that better explains other phenomenon but has anomalies in other models like the Kuhnian revolutions. So in many ways we're at a standstill in science. There's constant breakthroughs, but yeah, I think we're in the need of a new revolution in science. So kind of like the due diligence, I'm applying myself to the scientific method, and as opposed to saying like I have the answers and my answers are correct. Um, I'm more at the state like George Pierce said of irritation. I'm irritated by my inability to understand, and my inability to understand is because of these anomalies and these conflicting models that solve certain aspects, but are problematic for describing other aspects. So we have a bunch of theories. Some of the theories overlap, some of the theories contradict each other, and there's no universal way to explain the phenomenon, the theory of everything in terms of physics. There's some level of like a theory of everything to um like the for physics in terms of like the various forms of energy and unifying the various forms of the conservation of energy, but it's in terms like, is that really a theory of everything? Is it going to help in terms of the hard problem of consciousness or other things? That's unclear. And even the current state of machine facilitated science, where almost now all science is statistical methods that are ran through computer models. And at this point now, these computer models understand science better than we do. So the level of the scientist has to interpret the computer generated models. And what does that mean? Especially with the advances in I'm not like really chat GPT, but the associated technology of like AlphaFold, of AlphaZero, uh, that's similar to the chat GPT technology, but have been applied to science, most notably recently in terms of AlphaFold. But likely this technology will be applied to more and more scientific fields, and the computer will be able to demonstrate a superior understanding of the technology than mankind is able to understand. And like chess, and like I mentioned Herbert Simon some in the philosophy of technology. I actually want to come back to the chess research into the science of expertise. And also, so I have to thoroughly ground the philosophy of science to say, well, what is the science of expertise, and how am I calling such a thing the science of expertise? But in terms of like chess, where now the computers are substantially better than the top players, and most of the top players model their behavior after the computer. And the difference between the top chess players is that they have somewhat of a better conceptual understanding of why the computer says this is the best move. That a human player, may not have thought to think what the computer is the best move, but they know if the computer says it's the best move, it probably is. And the top players have a better understanding why the computer said so. In a similar way that I said, it would probably be like that with art, where top artists would have a better understanding of why the computer or how to generate art. But also maybe with fields like medicine, or even terms like theoretical science like AlphaFold, for what is the computer doing, why was the computer able to do what we weren't able to do, and possibly things like radiology, maybe the field of medicine, where based on a full examination of like a patient profile, a computer may be able to generate a better medical prognosis than a doctor. However, the doctor will have the best possibility of understanding why the computer unlikely will be able to explain why that's the best prognosis or how it came up with it. And you'll need the doctors to decipher it. And likely science is moving in that direction. So I got over 5 hours. Thanks, Nam Nam Wave more for um, Passenger Del Toro. Thanks for tuning in. Appreciate the viewers. So hope people are gaining from this. I'm gonna go on. Like I'm personally gaining from this, and hopefully people who watch Week in Review also. This will be like an addendum to Week in Review, so that we could push forward, and some of the due diligence that's necessary to push forward the ideas that is too much to actually do on Week in Review. So some of this hopefully will serve as an addendum to regular Week in Review watchers. So with that, God bless. Have a great night. And Week in Review should be tomorrow night at 7 p.m. ET. It could be the next few weeks. It's going to be Thursday night. Jennifer is having scheduling issues. So hopefully we're going to trying to continue with Week in Review, but it's bouncing around. So as of now, it's planned for tomorrow night at 7 p.m. and we just have to play it from there week by week. And you're depending on Jennifer's schedule. But in the meantime, I'm going to try to do these streams, um, which will, basically just, like if people come on and want to talk or are following it, I'm happy to have guests. But basically, it'd be me reading articles and kind of like discussing my thoughts on articles or tying together various themes in relationship to uh, the motivation for the multiple truth hypothesis and an eventual somewhat formulation of the multiple truth hypothesis and the utility of it. So, God bless. David signing off. Have a great night. Hope to see you tomorrow night, week in review, and the strength next Sunday and Wednesday for more.